Mars has endured countless celestial assaults over the ages. Asteroid impacts, relentless dust storms stretching across the planet's surface, and 4 billion years of cosmic bombardment from the depths of space. Yet despite these long-standing challenges, it has never faced anything quite like the enigmatic visitor known as 3IATLAS. This interstellar wanderer, carrying within it a cargo of ice and complex chemistry, was forged under the light of a sun unlike our own, a star from a distant alien system. Its approach toward Mars marks a pioneering moment for humanity, a first test of how well we truly understand the cosmic threats lurking beyond our familiar solar neighborhood. The encounter, scheduled for October 3, 2025, could simply be a routine gravitational ballet, a predictable cosmic dance where Atlas passes by at a safe distance and we observe from afar. Or perhaps more ominously, it could set off a chain reaction of catastrophes, impacting the planet itself, contaminating its environment with alien molecules, and transforming Mars from a potential new home into the most profound warning of our planet's vulnerabilities. The spectrum of possible outcomes is so wide that reliable prediction becomes nearly impossible, spanning everything from minor perturbations to planetary scale upheavals. Tonight, we will explore why the most disastrous scenario might not be an impact at all. Instead, the greatest threat could be something far more subtle. An insidious process that, once set in motion, could alter Mars forever, in ways that may be irreversible and hidden from immediate detection. Stay with us until the end, where we will reveal why the most alarming outcome might not involve impact at all, but a slow, creeping danger that could threaten the very fabric of the planet's stability. Let us begin with the significance of October 3, 2025. Mark this date in your calendar because it is a moment unlike any other that will occur in our lifetime, a rare celestial event that will not happen again. On what appears to be an ordinary Friday, an extraordinary event will unfold in the cold void between worlds, a cosmic ballet that could redefine our understanding of planetary safety and interstellar threats. The object in question, our mysterious visitor from beyond the stars, 3IATLAS, will whiz past Mars at a distance of roughly 30 million kilometers. In everyday terms, that seems comfortably remote. It's about 75 times the distance from Earth to our moon. Far enough to feel safe, distant enough to dismiss as insignificant. But in the realm of interstellar objects, this proximity is what astronomers call an uncomfortably close shave. It's a narrow margin, a cosmic near miss that demands the utmost scrutiny. The European Space Agency has been meticulously tracking this encounter with a level of precision usually reserved for defusing bombs or navigating asteroid threats. Their calculations depict a scenario that has a touch of celestial chaos, where the rules of orbital mechanics seem to have gone slightly awry. Atlas isn't behaving like the well-mannered comets we are used to seeing in our familiar solar system. Instead, it has been exhibiting signs of cosmic tantrums, erratic, unpredictable, and increasingly unstable. Since its first detection, evidence has been mounting like a gathering storm cloud on a summer horizon, warning us of potential trouble. For instance, Atlas has been generating a colossal carbon dioxide coma, an expansive billowing cloud of gas that extends millions of kilometers outward in every direction, creating a hazy shroud that obscures much of the comet's nucleus beneath an atmospheric cloak of alien molecules. Most comets, in comparison, tend to display such dramatic gas clouds only when they draw close to the sun, igniting their icy tails with warmth and solar wind. However, Atlas seems to have missed that typical etiquette of celestial behavior, appearing to shed its gaseous envelope far earlier and more aggressively than expected. This premature display hints at internal processes that are anything but normal, perhaps a sign of fundamental instability. Adding to the concern are the brightness surges observed by multiple telescopes and observatories worldwide. These are not gentle, predictable increases in luminosity that one might associate with a chunk of ice gradually warming in sunlight. Instead, they are sudden, unpredictable flare-ups, brightening and fading in a matter of hours, with no warning and no clear pattern. Such erratic outbursts are characteristic of something inherently unstable, perhaps a body held together by sheer cosmic willpower rather than structural integrity. The comet's behavior suggests it might already be on the brink of fragmentation, with its stability precariously balanced as it hurtles through the void toward Mars. NASA's SphereX telescope has been tirelessly tracking the mysterious anomalies associated with ATLAS, and the wealth of data it amasses paints a picture that would cause any planetary defense specialist to reach instinctively for their antacids. The shape and structure of the plume emissions, for instance, appear irregular and defy the expectations set by our current models. Its peculiar geometry suggests something is amiss. The patterns of gas emissions are erratic, following sequences that don't align with the well-understood behaviors of comets or interstellar objects as we know them. Even the orbit of ATLAS itself exhibits delicate perturbations, subtle shifts that hint this isn't merely a conventional dirty snowball from the distant icy outskirts of another star system. It's here that the situation takes a decidedly more alarming turn. The most concerning development emerges as ATLAS approaches what scientists politely call a visibility gap. This is the critical window known as solar conjunction, when the alignment of Mars, the Sun, and Earth occurs in such a way that our ability to observe and monitor the object becomes severely hindered. During this phase, the Sun's intense brightness and electromagnetic interference effectively blind our telescopes, making clear observation nearly impossible for several weeks. The timing couldn't be more ominous. Just as ATLAS reaches its closest point to Mars, the phase during which it could trigger the most dramatic and potentially catastrophic interactions. Our monitoring capabilities are practically non-existent. Pause for a moment to grasp the gravity of this situation. It's akin to trying to watch a high-stakes poker game through a tiny keyhole while wearing a blindfold. The most critical moment, the one when ATLAS is at its most perilous proximity to Mars, happens precisely when we are left in the dark. It's as if the universe, with its inscrutable sense of irony, has conspired to keep us in suspense, testing our preparedness and resolve. The cosmic chessboard is set, and we can only hope we're making the right moves despite not knowing the opponent's next move. This timing appears far too convenient, suspiciously so, as if orchestrated by some malevolent cosmic intelligence aiming to maximize our vulnerability. The universe seems to have a twisted sense of humor when it comes to concealing the true fate of our neighboring planet. Meanwhile, the scientific community finds itself walking a razor's edge, balancing on the fine line between cautious skepticism and barely contained panic. They are acutely aware that rapid and unpredictable activity changes in comets often serve as early warning indicators of impending fragmentation events. When a comet begins behaving erratically, its coma suddenly brightening without warning, its emission patterns becoming chaotic and unpredictable, experienced astronomers know that it's time to brace for possible disintegration. The spectacle of a comet breaking apart in the depths of interstellar space is one thing, but the thought that such a fragmentation could happen within the very neighborhood of Mars just a few million kilometers away is altogether a far more disturbing proposition. Now imagine that very event occurring not in the safe, distant reaches of interstellar space, but dangerously close to Mars itself. Visualize colossal chunks, perhaps spanning entire kilometers, ancient ice and rock, suddenly being liberated from their parent body. These fragments, each a miniature asteroid on its own, would then follow their own unpredictable trajectories through the complex gravitational web of the inner solar system. Some might spiral sunward, adding to the increasing population of potentially hazardous debris. Others could be deflected onto collision courses with planets, including Mars, which has spent billions of years in a tranquil, unperturbed state. The European Space Agency's models suggest a grim future. Even without a direct impact, the gravitational disturbances caused by such a fragmentation event could be enough to steer some debris onto orbits that intersect with Mars's path. These fragments could remain on collision courses for years, even decades, effectively turning Mars's neighborhood into a sprawling minefield of cosmic hazards. What's truly unsettling is the realization that we may be witnessing not just a single close encounter, but the beginning of a long-lasting seeding process, an insidious cosmic minefield that could complicate exploration efforts and human missions for generations. Adding to the unease is our profound ignorance about Atlas's true nature. The colossal coma enveloping the object obscures our view of its core, its nucleus, leaving us uncertain whether we are dealing with a single, massive, loosely held together object or a fragile conglomeration of fragments already barely bound by gravity. It could even be something far more exotic, an engineered or artificially manipulated object, cloaked in its gaseous shroud. This uncertainty only deepens the mystery, making the impending approach a potential source of unforeseen chaos. The lack of clarity about what precisely Atlas is, whether a rogue single body or a chaotic collection of debris, amplifies the sense of looming danger and leaves scientists grappling with an unsettling ambiguity at the heart of the unfolding scenario. The luminous, shimmering shroud that envelops Atlas, making it such a visually breathtaking spectacle, may conceal a far more perilous secret. A cosmic time bomb whose eventual detonation could send a cascade of debris sprawling across multiple planetary orbits. Such a catastrophic dispersal could threaten not just Mars but the entire inner solar system, transforming serene celestial neighborhoods into chaotic fields of perilous fragments. In the face of this looming threat, NASA's Science Mission Directorate has been notably reticent about outlining concrete contingency strategies. Officially, no detailed plans have been publicly disclosed, yet insiders within the agency suggest a carefully coordinated effort to position multiple orbiters around Mars. The goal is clear: to capture critical data during the potential encounter with Atlas, regardless of what unfolds. Among these robotic sentinels are the Mars Reconnaissance Orbiter, the MAVEN spacecraft, and the European Space Agency's Trace Gas Orbiter, our collective eyes and ears stationed at the Red Planet. These sophisticated instruments are designed to monitor Mars's environment and gather invaluable scientific data, but their capabilities are tailored for routine observation, not for high-velocity cosmic debris tracking. If Atlas decides to stage a dramatic spectacle, a sudden burst of activity, a fragmentation event, or even an impact, these robotic explorers will be our only witnesses. Their data could be pivotal, reshaping our understanding of interstellar visitors and the risks they pose. Yet even these highly advanced devices face inherent limitations. Their camera systems and spectrometers were engineered primarily to analyze Mars's surface and atmosphere, not to track fleeting high-speed cosmic fragments hurtling through space at velocities that defy conventional detection methods. Their communication systems are optimized for steady data relay, not for emergency broadcasts in the face of planetary catastrophe. Should Atlas choose to unleash a cosmic firework display, fragmenting in a spectacular, unpredictable fashion, our Mars-based assets might find themselves woefully unprepared for the chaos. Their sensors could be overwhelmed, their data streams interrupted or rendered useless in the face of intense electromagnetic disturbances, high-velocity debris, and rapidly evolving atmospheric effects. The promise embedded in this investigation extends far beyond mere scientific curiosity. It is a venture into the unknown, an inquiry that could reveal vulnerabilities in our planetary defense systems and challenge our assumptions about cosmic safety. We are committed to following the evidence wherever it leads, even if it guides us into treacherous territories that render our current notions of planetary security dangerously naive. We will scrutinize the collision scenarios that keep planetary defense specialists awake at night, pondering whether our defenses are sufficient against the unpredictable nature of interstellar visitors. We will explore atmospheric effects that could turn Mars into a toxic wasteland, with dust storms infused with radioactive particles or chemical contaminants that could jeopardize future colonization efforts. The possibilities of biological or chemical contamination spreading through the planet's atmosphere or surface could complicate humanity's long-term plans for Mars for centuries to come. Most critically, we will confront the questions that official agencies seem hesitant to voice publicly. What if Atlas isn't merely passing by on a benign trajectory? What if October 3rd marks the onset of something far more sinister? A cosmic event that could alter the fate of Mars and perhaps the entire solar system. The answers to these questions may not only surprise you, they could terrify you. But one certainty remains. After October 3rd, our relationship with interstellar visitors will never be quite the same. The collision scenarios we are about to explore are merely the tip of a vast icy iceberg, the part visible above the surface, while beneath lies a deeper realm of planetary catastrophe and cosmic upheaval that most minds dare not imagine. Part 2. The collision scenario. The mathematics underlying cosmic destruction, surprisingly, are elegant in their simplicity. When astronomers attempt to estimate the likelihood of Atlas actually colliding with Mars on October 3rd, the initial calculations seem reassuring. At a distance of roughly 0.19 to 0.2 astronomical units, about 17 to 18 million miles, geometric considerations suggest that a direct impact is, statistically speaking, highly unlikely, bordering on the impossible given natural orbital dynamics. However, as with many aspects of celestial mechanics, the devil is in the details. Mathematics, much like democracy, functions optimally only when its rules are obeyed by all involved. And, as established, Atlas appears to be something of a cosmic rebel, an interstellar object that behaves unpredictably, defying conventional expectations. Now consider what might happen if one of those mysterious fragmentation events previously discussed occurs at precisely the wrong moment when Atlas is closest to Mars. A sudden chaotic breakup, triggered by internal chemical reactions, thermal stresses, or even an impact with unseen debris, could send a flurry of fragments hurtling toward the red planet. The timing of such an event could be catastrophic, transforming a distant, manageable risk into a planetary disaster in the blink of an eye. Imagine a colossal fragment, perhaps between 100 and 500 meters across, roughly the size of a bustling city block, hurtling toward Mars at an astonishing velocity, so rapid that even the swiftest rifle bullet would seem sluggish in comparison. This piece of cosmic debris, born from a catastrophic breakup of an interstellar visitor that had held itself together for 30,000 years, would strike with an unimaginable force. The kinetic energy unleashed by such an impact would be equivalent to the detonation of thousands of nuclear weapons occurring simultaneously, a force capable of carving a crater several kilometers across the Martian surface. But this initial scar, dramatic as it is, would merely mark the beginning of the planet's upheaval. Mars's atmosphere, thin and primarily composed of carbon dioxide, offers almost no defense against such incoming projectiles. Unlike Earth's thick, protective atmospheric blanket that can incinerate smaller objects or slow larger ones down, Mars presents a vulnerable target, almost as if it were exposed to cosmic assault without armor. The vast energy of the impact, instead of being absorbed or dissipated by atmospheric friction, would be directly transferred to the planet's crust with relentless fury. The immediate result would be a world transformed, an alien landscape utterly unrecognizable from the Mars we have studied for decades. Debris from the impact, shattered rock, pulverized ice, and ancient permafrost would be ejected high into the planet's already tenuous atmosphere, igniting a planet-wide dust storm of unprecedented scale. This chaos would dwarf even the most ferocious seasonal storms observed on Mars, turning the sky into a swirling opaque curtain that could last for days, weeks, or even months. Within hours, the entire surface would be cloaked in a choking haze of suspended particles, blocking out sunlight and dimming the once bright landscape. Solar-powered explorers, rovers, and landers would find themselves starved of the energy they depend on, rendered useless in the face of this relentless dust storm. The effect on Mars's climate would be profound. Temperatures would plummet as the dust layer reflected and absorbed incoming solar radiation, creating a brutal, prolonged winter that could extend for months or years, a kind of planetary nuclear winter. The familiar rhythms of Martian seasons would be shattered, replaced by chaos and darkness. But perhaps even more alarming than the dust clouds would be the electromagnetic aftermath of such an impact. The explosion would generate intense electromagnetic pulses, powerful bursts of energy resulting from charged particles interacting with Mars's weak magnetic field. These pulses could induce damaging electrical currents in the delicate electronic systems of orbiting spacecraft. Our robotic sentinels, such as the Mars Reconnaissance Orbiter MAVEN and Mars Express, would suddenly find themselves operating in an environment far more hostile than anything their engineers had anticipated. Their sensitive instruments, designed for routine scientific exploration, could be overwhelmed or permanently damaged by the electromagnetic chaos unleashed by the impact. In this new, turbulent environment, these orbiters would be vulnerable to signals of disruption, radio interference, power surges, and calibration failures, potentially crippling our ability to monitor and analyze Mars's evolving condition. The once reliable links that have allowed us to communicate with our robotic explorers would be severed or rendered erratic, leaving us in the dark about the true extent of the planet's transformation. It would be a scenario of technological chaos, an unanticipated disaster that could delay or even halt future missions, forcing us to confront the limits of our current spacefaring capabilities amid the chaos of cosmic violence. The technological marvels currently orbiting Mars, star trackers, communication arrays, and solar panels, face an onslaught of cosmic chaos should a significant impact occur. Star trackers, which rely on the observation of stellar positions to maintain precise orientation, could become blind amidst a cloud of ionized debris, losing their ability to guide spacecraft accurately. Meanwhile, the radio communication systems designed to transmit data across the thin Martian atmosphere might be overwhelmed by relentless radio interference generated by charged particles and turbulent plasma clouds. Solar arrays tasked with harvesting sunlight could suffer severe damage from high-velocity particles accelerated during the impact, causing them to degrade or fail entirely. On the Martian surface, the consequences would escalate from disruption to disaster. While robotic explorers like Perseverance and Curiosity are engineered to withstand typical dust storms, those seasonal, often predictable tempests, an entire planet's worth of dust whipped into a hurricane by a cosmic impact would constitute an entirely different challenge. Such a planet-wide dust storm would obscure the sky and interfere with radio transmissions, rendering communication with Earth sporadic or entirely severed. The atmosphere, already tenuous and thin, would be further disturbed. The impact would excavate subsurface materials, lofting vast quantities of dust, ice, and debris high into the atmosphere and creating a turbulent, chaotic environment. This upheaval would cause the radiation environment around Mars to spike dramatically. The impact's excavation of subsurface layers would release charged particles and radioactive materials, saturating the atmosphere with ionized debris. With Mars's weak magnetic field and minimal atmospheric shielding, both of which provide only limited protection against radiation, the planet would become a hazardous zone for any future human explorers. The surface radiation levels would soar, creating lethal conditions that could jeopardize both human missions and robotic systems. Even the most resilient machines designed to endure the harsh Martian environment would face an increased risk of radiation-induced failures, further complicating any rescue or recovery efforts. Now take this scenario and amplify it to a truly apocalyptic scale. Instead of a solitary fragment, imagine multiple pieces of Atlas, each traveling at interstellar velocities, reaching Mars and producing not just one, but dozens of city block-sized projectiles. The cumulative effects of such fragmentation would be catastrophic. Overlapping clouds of ejecta and debris would blanket the planet, transforming it into a tumultuous storm of rocky fragments and dust. The electromagnetic effects of this chaos would be profound, creating electromagnetic pulses and radio blackouts that could last for months, severing the planet's electronic lifelines. The dust itself would reach such densities that it could entirely block incoming solar radiation, plunging Mars into a planetary ice age that might last for centuries. This prolonged climatic shift would redefine the planet's habitability and make future colonization efforts exceedingly difficult. Meanwhile, the gravitational chaos unleashed by multiple impacts would threaten the stability of Mars's two small moons, Phobos and Deimos, which are already on unstable trajectories. Phobos, which is slowly spiraling inward toward its planet, is predicted to crash into Mars in roughly 50 million years. However, a major impact could accelerate this process dramatically. Sufficient force delivered to Phobos or gravitational perturbations from the impact fragments could destabilize its orbit, leading to the moon's destruction in real time. The debris from such a moon-shattering event would not simply fall into Mars's surface, but would instead form a chaotic, irregular ring system, an unstable, jumbled array of rocky fragments orbiting the planet. Unlike the graceful rings of Saturn, this Martian debris ring would be a hazardous, unpredictable environment, posing navigation hazards for centuries and rendering the planet's orbit and surface terrain even more treacherous for future missions. The psychological impact on humanity watching from afar would be profound. Mars is our next frontier, our backup for the future, and a symbol of our spacefaring aspirations. To see it transformed into a radiation-soaked wasteland, surrounded by a chaotic debris ring, would be a devastating blow. An unfolding disaster that signifies the loss of our planetary outpost and the beginning of a new era of cosmic vulnerability. It would be like witnessing our future crumble in real time, a stark reminder that even our most ambitious aspirations remain fragile against the unpredictable might of the cosmos. Even this catastrophic scenario, with its apocalyptic imagery of impact and chaos, appears insignificant when weighed against a far more subtle and potentially irreversible threat. One born not from direct collision, but from the insidious effects of electromagnetic and particle interactions. What if the true danger from the October 3rd encounter with Atlas isn't a rock or ice fragment striking Mars, but something far more elusive? Something capable of poisoning the very environment that could one day support human life. Mars's defenses against cosmic assaults are, to put it kindly, woefully inadequate. Unlike Earth, which is shielded by a vast protective magnetic cocoon that deflects most charged particles emanating from the sun and beyond, Mars remains largely exposed. Its ancient magnetic field, which once enveloped the planet in a protective shield, has long since faded away. Today, only scattered magnetic anomalies remain, fossilized scars of a bygone era, testament to the planet's former defenses. Without a global magnetic field, Mars is exposed, vulnerable, and exquisitely susceptible to the effects of energetic particles and electromagnetic disturbances that Earth's magnetosphere would shrug off effortlessly. When Atlas sweeps past Mars, trailing its enormous coma of carbon dioxide and possibly shedding debris into the void, it doesn't deliver a conventional impact in the Hollywood sense. No thunderous shockwave racing across the landscape at supersonic speeds. Instead, what we're dealing with could be a far more subtle and insidious form of destruction. An electromagnetic cascade, a complex interplay of charged particles and plasma that could, over time, fundamentally alter the planet's atmospheric chemistry and electrical environment. Imagine Atlas as it approaches Mars, its nucleus venting gases and particles in chaotic, irregular bursts. Discharges that we've been meticulously tracking throughout the year 2025. Each of these outbursts expands into clouds of ionized plasma, creating a dynamic environment that interacts with the solar wind in unpredictable and complex ways. As this ionized cocktail encounters what remains of Mars's weak magnetic remnants, it doesn't simply bounce away. Instead, it penetrates, swirls, and generates electromagnetic eddies, chaotic, turbulent fields that could linger long after Atlas has moved on, continuing to influence Mars's space environment. The immediate consequence of such interactions might be a dramatic intensification of phenomena that are, at present, barely noticeable. Auroras so faint they are almost invisible, localized and sporadic. But in this scenario, the auroras could evolve into planet-wide displays, braided curtains of chaotic charged light that shimmer across the entire Martian sky. These storms of electromagnetic energy wouldn't be the gentle, picturesque northern lights that Earth's polar regions enjoy. They would be wild, chaotic phenomena, sinister storm clouds of light that interfere with radio signals, distort electromagnetic signals, and pose a real threat to the electronic systems vital for future exploration and potential colonization. Yet the visible disruptions are merely the surface phenomena, the tip of the iceberg. Beneath this lies the real danger, the destabilization of Mars's ionosphere, the electrically charged layer of the upper atmosphere that our orbiting spacecraft depend on for communication. This delicate layer, crucial for relaying signals between robotic explorers and Earth, could become a battleground of electromagnetic chaos, with cascading effects that might persist for months or even years, long after Atlas has vanished into the depths of space. The consequences of this unseen electromagnetic turmoil could be profound, altering the very fabric of Mars's atmospheric environment and rendering future human missions increasingly perilous. As Atlas's charged particles begin to interact with the Martian environment, they would ignite a cascade of electromagnetic effects that could have profound and far-reaching consequences. One of the most immediate and alarming outcomes would be the formation of radio blackout windows, periods that could extend for weeks, during which communication between Earth and the robotic explorers on Mars would be completely severed. These blackout phases would pose a significant threat to our carefully orchestrated operations, as the robots, such as the rovers Perseverance and Curiosity, have become accustomed to reliable scheduled exchanges with mission control. These sessions are meticulously planned, allowing the robots to upload vital scientific data and receive new instructions necessary for their ongoing missions. If Atlas's electromagnetic influence disrupts the ionosphere, these vital links could be cut, leaving billions of dollars worth of advanced machinery effectively stranded on a distant alien world. Without the ability to transmit data or receive commands, these robotic sentinels would become silent witnesses, unable to report their status or adapt to evolving conditions, essentially turning into lost explorers adrift in an environment that is rapidly becoming hostile. But the electromagnetic chaos would not be confined solely to the ionosphere. Mars's atmosphere, which is remarkably thin and primarily composed of carbon dioxide, makes it exceptionally vulnerable to electrostatic phenomena. Effects that would be barely perceptible on a planet with a denser, more protective atmospheric envelope like Earth. As Atlas's debris field interacts with the Martian atmosphere, it could generate conditions akin to the massive dust devils that already sweep across the planet. Except now, these would be magnified to an extraordinary degree, supercharged with electrical energy. Imagine colossal dust storms where individual particles carry substantial electrical charges, creating lightning discharges that would make any terrestrial thunderstorm seem tame by comparison. These lightning arcs wouldn't be the gentle static discharges that occasionally flash across Earth's skies. They would be violent, jagged bolts of electrical energy capable of physically damaging surface equipment, from landers and sensors to power systems. Furthermore, these electrically charged dust storms could produce intense radio frequency interference, effectively drowning out signals sent to and from Earth. The resulting communication blackout would not only hinder real-time data transmission, but could also disable the ability to coordinate rescue or repair efforts, rendering surface operations nearly impossible. The scenario becomes even more unsettling when considering Mars's natural tendency for global dust storms. These planetary-scale tempests can ignite seemingly from minor triggers, small temperature differentials or pressure fluctuations, yet once underway they can envelop the entire planet for weeks or months. The electromagnetic chaos unleashed by Atlas's passage could act as the catalyst, providing the precise spark needed to push Mars's atmosphere into a state of unrelenting chaos, spiraling into a catastrophic planetary storm. But the potential for disaster deepens when we consider the physics of planetary weather. What if Atlas's charged debris doesn't merely trigger a standard dust storm, but instead sets off a completely novel atmospheric phenomenon? Something that would be recorded in the annals of planetary meteorology as unprecedented. The combination of charged particles from Atlas's coma and the existing atmospheric dynamics of Mars could create a feedback loop, a self-sustaining cycle of electrical and meteorological upheaval. Envision this as a nightmare scenario. The initial electromagnetic disturbances generated by the influx of charged debris would produce static electricity in the upper atmosphere. This static would then transfer to dust particles, charging them and making them more susceptible to becoming airborne. As these dust particles become energized, they would absorb and scatter solar radiation differently, altering the planet's energy balance. These changes would generate temperature and pressure differentials, fueling the storm further and making it intensify. Simultaneously, the charged dust particles would continue to interact with what little of Mars's magnetic field remains, scattering, spiraling, and perpetuating the electromagnetic chaos. This interaction could lead to a situation where the planet is trapped in a quasi-permanent state of electromagnetic and meteorological turmoil. The storm, fed by a relentless feedback loop, might persist for years, long after Atlas has moved on toward the distant reaches of the solar system. During this prolonged period of planetary upheaval, the Martian surface would be subjected to intense electrical activity, with lightning strikes and electrical discharges occurring more frequently and more violently than anything previously observed. This scenario paints a picture of a planet caught in a relentless cycle of chaos, a feedback loop from hell, where electromagnetic and meteorological disturbances reinforce each other, creating a self-sustaining storm system. The implications are dire. Surface equipment could be damaged or rendered inoperative. The atmosphere could become increasingly hostile, and even future human explorers might find themselves facing a planet that is fundamentally transformed. An environment where electrical storms and dust clouds rule the skies for years, if not decades. The persistent electromagnetic turbulence would also pose a significant threat to the delicate electronic systems of any future missions, amplifying the risks of exploration, colonization, and scientific research on Mars in the aftermath of Atlas's passage. Mars could transform into a planet of relentless chaos, where endless dust storms swirl ceaselessly, shrouding the landscape in a perpetual haze. The atmosphere would be riddled with charged particles and charged dust clouds, creating a turbulent environment that would make reliable radio communication nearly impossible. Even the most resilient robotic explorers designed to withstand the harshities of the Martian surface might find themselves succumbing to electronic failures induced by electromagnetic interference and electrical discharges. NASA's spacecraft engineers have long prepared for a variety of challenges associated with operating on Mars, including dust storms, radiation, and communication blackouts. However, they have never faced a scenario akin to a planet-wide electromagnetic tornado, a chaotic maelstrom of charged particles and magnetic disturbances sweeping across the entire planet. The high-gain antennas of orbiters like the Mars Reconnaissance Orbiter might be caught in a constant battle, struggling to maintain a stable connection amid the relentless interference from charged dust clouds buffeted by electromagnetic storms. MAVEN's particle detectors, which are calibrated to analyze the gentle interactions between the solar wind and Mars's upper atmosphere, could be overwhelmed, flooded with a chaotic environment of charged particles that defies our current models. The immediate aftermath of such an event would be a public relations nightmare of unprecedented proportions. As images from the Martian surface become sporadic and communication windows vanish, a wave of speculation and fear would grip the global consciousness. Social media platforms would be flooded with theories ranging from plausible scientific explanations to wild conspiracy narratives about what is truly happening to our robotic emissaries on the Red Planet. Official sources, constrained by the need for caution, would issue technical explanations and reassurances, but these would be drowned out by sensational stories claiming cosmic catastrophes or secret government cover-ups. Perhaps the most unsettling aspect of this electromagnetic nightmare is how it would be grossly misunderstood by the general public. Mars would not be on fire in any literal sense. Carbon dioxide, the primary component of its atmosphere, does not support combustion like oxygen does. Nonetheless, the planet's skies might be illuminated by dazzling auroras and frequent lightning discharges from charged dust storms. Visual phenomena caused by electromagnetic interactions could be mistaken for signs of planetary destruction. The eerie electromagnetic displays and violent lightning would craft a spectacle that, to untrained eyes and a media hungry for sensationalism, could appear as a planet in flames or a catastrophic inferno. Meanwhile, the scientific community would find itself in an awkward, delicate position. They would have to clarify that Mars has not literally ignited, while simultaneously acknowledging that the planet has become temporarily uninhabitable for human explorers and robotic missions. The difference between actual chemical combustion and electromagnetic chaos would blur in the public eye, especially given decades of disaster movies and sensationalist media that have conditioned audiences to interpret cosmic events as apocalyptic. Yet, even as we grapple with the nightmare of electromagnetic storms, we must consider that this chaos might not be the most severe risk posed by Atlas. What if the comet brings with it something far more persistent and insidious, something that endures long after the electromagnetic disturbances fade? What if the true danger lies not in the physical or chemical disruptions but in biological contamination? A form of alien life, hitchhiking on cosmic debris from another star system, could find its way to Mars, threatening not just the planet's immediate future but our entire long-term relationship with the Red World. This contamination scenario operates on timescales vastly different from electromagnetic storms, timelines that make a summer squall seem fleeting. Unlike electromagnetic disturbances that might last weeks or months, biological contamination could persist for centuries or even millennia, fundamentally altering the course of Mars's evolution and our plans for colonization. Part 4. Contamination from another star. The idea of panspermia, the hypothesis that life or its building blocks are transported between worlds via cosmic debris, has captivated scientists for decades. It suggests that life might not have originated solely on Earth but could have been carried across the cosmos on meteorites, comets, or other celestial fragments. When that cosmic debris originates from a different star system, however, the implications become far more profound and potentially perilous. If an interstellar object like Atlas carries within it molecular cargo from a stellar environment completely alien to our solar neighborhood, the risk of biological contamination becomes a genuine concern. Such debris might harbor complex organic molecules, bacteria, or even primitive life forms that have adapted to conditions unlike anything on Earth or Mars. The transfer of biological material across interstellar distances would represent a form of cosmic hitchhiking, one with potentially devastating consequences. The potential for interstellar contamination raises challenging questions about planetary protection and the long-term safety of exploring or colonizing Mars. While our current protocols are designed to prevent contamination from spacecraft within our solar system, they are based on the assumption that objects and biological materials originate from within that system. An interstellar object like Atlas, however, bypasses these safeguards, bringing with it a cargo of alien molecules that could interact unpredictably with Mars's environment. Once deposited on Atlas offers us a chilling and often unspoken possibility that the scientific community tends to shy away from publicly confronting. This extraordinary interstellar traveler has, over the course of at least 30,000 years, journeyed silently through the vast cold depths between the stars. Its core, acting much like a cosmic deep freeze, has preserved a delicate cargo of molecules, biological or chemical signatures that it may have accumulated during its long voyage through an alien stellar system. Among the myriad of gases enveloping this object, the most prominent has been a colossal cloud of carbon dioxide, which Atlas has continuously generated as it travels. This dense, expansive coma creates an environment rich in the right conditions, chemically perfect for complex organic molecules to not just survive but potentially to undergo processes of evolution during this interstellar passage. This isn't merely a matter of waste gas. Carbon dioxide is far more than that. It is an exceptional solvent that can facilitate organic chemistry, stabilizing intricate molecular frameworks across a vast range of temperatures and pressures that Atlas has endured in the depths of space. This chemical environment could serve as a natural incubator for molecules that, under different circumstances, might give rise to life or at least mimic biological activity. NASA's James Webb Space Telescope has been diligently analyzing Atlas's coma through spectroscopic methods, attempting to decode its chemical composition from afar. However, the initial results are frustratingly tentative. They provide only a partial picture. The infrared signatures identified so far confirm the presence of familiar molecules, carbon dioxide, water vapor, and more intriguingly, what the mission scientists carefully describe as complex organic species. Yet what exactly these organic components are remains shrouded by layers of technical complexity, peer review, and interpretative uncertainty that could take months or even years to fully unravel. Meanwhile, the SphereX mission, tasked with close surveillance, has been monitoring subtle variations in Atlas's emissions. These variations suggest that what we are witnessing may not be simple sublimation, the process of frozen gases turning directly into vapor, common among comets warming as they approach the sun. Instead, the detected patterns seem to hint at ongoing chemical reactions within the coma itself. Reactions possibly catalyzed by cosmic radiation penetrating the coma or by internal chemical processes slowly unfolding during the object's interstellar trek. These processes could be more dynamic and complex than initially assumed, pointing to a chemistry that is active and evolving, not static or purely physical. What makes this scenario even more astonishing and potentially alarming is that current planetary protection protocols designed to safeguard celestial bodies from biological contamination were developed solely for missions within our solar system. These procedures focus on preventing terrestrial microorganisms from hitchhiking to other planets or moons. They assume a context where spacecraft are sterilized and ecosystems are contained. But no one has seriously contemplated what might happen if an entire ecosystem, an alien biochemical system, arrives at Mars unsterilized, uncontained, and in a state of active chemical flux. Such an event could deliver organic molecules to Mars that have never existed within its natural environment or in our solar system's history. These molecules might have evolved under the unique chemical conditions of an alien stellar system, making their interactions with Martian soil and atmosphere entirely unpredictable. The potential consequences are profound. These extraterrestrial compounds could catalyze unforeseen reactions, altering the delicate chemical balance that has persisted on Mars for billions of years. They might act as molecular templates, structure templates that could interfere with our ongoing and future efforts to detect indigenous Martian life forms. Instead of simply adding new variables, these exotic molecules could initiate complex, self-sustaining chemical processes, pseudo-biological systems that might consume resources, spread, and alter the local environment in ways that challenge our understanding and our ability to distinguish native Martian life from contamination. Envision, if you will, a nightmare scenario where these alien organic molecules from Atlas seamlessly integrate with Martian regolith. They begin to self-organize, creating structures that mimic biological processes, tentative, active, and disturbingly unpredictable. These structures might not be alive in the conventional sense, lacking metabolism or reproduction as we define them, but could nonetheless modify local chemistry, consume resources, and propagate through environmental mechanisms. Such activity might be subtle at first, but over time it could grow into a persistent, pervasive, and fundamentally foreign biochemical system, one that blurs the line between natural Martian processes and alien interference, and that challenges our entire approach to planetary protection and the search for indigenous life. The potential for pseudo-biological activity induced by Atlas could render Mars inhospitable to human colonization long before we develop the necessary technologies for establishing permanent settlements there. Envision the daunting challenge of attempting to operate life support systems on a planet where the very soil has been tainted with self-replicating chemical processes. Complex reactions whose origins, mechanisms, and implications remain beyond our current understanding and control. Such contamination would force a complete overhaul of our risk assessments and mission planning, demanding that we rethink every assumption about the planet's environment and our capacity to safely explore it. Even more troubling is the prospect of false positives in future efforts to detect life. Mars exploration has historically been fueled by the tantalizing hope of uncovering evidence, whether fossilized remnants or active biological processes, that hints at past or present life. The sophisticated instruments currently in development for upcoming Mars sample return missions are meticulously calibrated to identify faint chemical signatures that could suggest biological activity. But what if, during these investigations, the same instruments stumble upon organic molecules that originated from Atlas? How would scientists differentiate between indigenous Martian biochemistry and molecules introduced from an interstellar visitor? This dilemma presents a profound challenge. The risk of misinterpreting cosmic contamination as signs of native life could set back our understanding of Mars by decades, forcing researchers into painstaking efforts to disentangle genuine local signals from cosmic noise. The complexity of this contamination scenario deepens when we consider the potential for atmospheric dissemination. Should Atlas's approach trigger the kind of global dust storms previously discussed, organic molecules deposited on the Martian surface could become lofted into the atmosphere and carried across the entire planet in a matter of weeks. What might start as a localized contamination event, perhaps confined to a specific landing site, could rapidly evolve into a planet-wide phenomenon, spreading organic compounds indiscriminately and complicating future missions. Every subsequent landing, whether for scientific exploration or human habitation, would be compromised by this pervasive contamination, challenging the integrity of planetary protection protocols and raising questions about the true environmental state of Mars. NASA's current trajectory for Mars exploration includes bold plans for human missions in the third decade of this century. These ambitions hinge on the assumption that Mars offers a relatively predictable environment, where life support systems can operate reliably and in situ resource utilization, such as extracting water, oxygen, and fuels, can be effectively implemented to sustain long-term human presence. However, the organic contamination potentially introduced by Atlas threatens to undermine these foundational assumptions. Water extraction systems could become clogged with alien organic compounds, rendering them ineffective or even hazardous. Atmospheric processes, which are already delicate, might be overwhelmed by unforeseen chemical reactions catalyzed by interstellar molecules, reactions that our current models and engineering protocols were never designed to anticipate. The psychological toll on future crews could be equally devastating. Imagine being among the first humans to step onto Mars, only to realize that the planet beneath their feet has been fundamentally altered by the arrival of an interstellar visitor. The realization that contamination, unknown, uncontrolled, and potentially irreversible, has compromised the very environment humanity hoped to inhabit could shatter morale and trust in our exploration endeavors. The timeline for fully understanding the scope and impact of this contamination might extend over decades, as chemical and biological changes often unfold on long, slow scales. Unlike impact craters or electromagnetic disturbances whose effects are apparent within months or years, chemical and biological contamination might only reveal its full extent after many generations, possibly not becoming clear until the early 22nd century or beyond. This prolonged uncertainty places the scientific community in a particularly uncomfortable position. Discussing these possibilities openly involves navigating sensitive questions about planetary protection, ethics, and the future of human space exploration. The prospect of contaminating another world, potentially with alien life or self-replicating molecules, raises moral dilemmas that challenge current international treaties and protocols. Balancing the imperative to explore and understand Mars against the risk of irreversible contamination requires a level of caution and transparency that may be difficult to achieve amidst the pressures of ambitious space programs and public expectations. Recognizing the potential for biological contamination from interstellar objects might be construed as alarmism, possibly casting a shadow over the extensive support and investments that have gone into Mars exploration, endeavors spanning decades and costing billions of dollars. Such acknowledgement could be perceived as unnecessarily fueling fears that might undermine public enthusiasm and political backing. However, choosing to overlook or dismiss these risks is a perilous gamble, as it could leave future missions dangerously unprepared for environmental conditions that diverge significantly from our current projections and models. The existing body of international space law offers scant guidance for scenarios involving the contamination of celestial bodies by extraterrestrial biological materials. The Outer Space Treaty and subsequent agreements were originally crafted with the intent of preventing terrestrial microorganisms from hitchhiking to other planets, a concern rooted in human-made contamination within our solar system. They did not envisage or adequately address the possibility of cosmic delivery. An interstellar visitor like Atlas bringing alien chemistry and microbial life from beyond our stellar neighborhood. Should Atlas indeed introduce foreign biological materials to Mars, there exists no comprehensive legal framework delineating responsibility, liability, or coordinated response measures among nations. This scenario raises profound ethical questions about our planetary stewardship and moral authority. Do we possess the right to continue exploring and potentially contaminating Mars when such actions could jeopardize the planet's pristine environment? Should we postpone or halt future missions until we have a clearer understanding of what Atlas might have deposited, whether organic molecules, microbes, or other extraterrestrial substances, on the red planet? These are not merely technical or scientific questions. They strike at the core of our moral responsibility and could fundamentally reshape humanity's approach to space exploration for generations to come. As we grapple with these biological nightmares, we must also remember that Atlas operates within a domain governed by the laws of physics, laws that can become chaotic and unpredictable under certain conditions. The intricate gravitational dance involving planets, moons, and wandering cosmic debris follows principles that, under the influence of interstellar objects, can produce outcomes far more dramatic and destabilizing than issues of contamination alone. Imagine a scenario where the encounter with Atlas on October 3rd doesn't just alter Mars's surface chemistry or atmospheric composition, but triggers a cascade of gravitational disturbances that threaten the stability of the entire Martian system. This could mean the disruption of the finely balanced orbital relationships that have maintained the current configuration of Mars, its moons, and surrounding debris for billions of years. The chaos scenario we are about to explore operates on a scale so vast that biological contamination, though dangerous, is almost trivial in comparison. Part 5 delves into the realm of orbital chaos. Mars' two small moons, Phobos and Deimos, are often described by astronomers as captured asteroids, irregular fragments of rock that Mars managed to gravitationally ensnare in its distant past. Yet these celestial prisoners are far from simple or predictable. Phobos, the larger and closer in of the two, is already on a slow, inexorable journey toward a collision with Mars, with an estimated timeline of approximately 50 million years before impact. Under normal circumstances, this timeline offers humanity ample opportunity to establish a presence on Mars and develop strategies to mitigate or adapt to the eventual moon crash. However, the approach of Atlas on October 3rd introduces a host of variables that could radically accelerate this cosmic deadline. The gravitational influence exerted by Atlas during its passage, while seemingly insignificant at a distance of 30 million kilometers, presents an intriguing paradox. At that distance, the comet's direct gravitational pull on Phobos and Deimos would be negligible, comparable in a rough analogy to the force exerted by a large building on Earth trying to influence the orbit of the Moon. Nonetheless, the subtle gravitational perturbations introduced by this interstellar visitor could act as a catalyst for a chain reaction of orbital instability, with consequences far beyond what straightforward calculations might suggest. Mathematically, the idea that Atlas could extend unseen tendrils to seize Mars's moons and violently redirect their orbits is simply unsupported by current models of celestial mechanics. Yet chaos theory reminds us that even the tiniest influences can cascade into monumental consequences when systems teeter on the brink of critical transitions. Phobos, the larger and closer of Mars's two moons, exemplifies this delicate balance. It exists in a state of gravitational vulnerability so acute that it responds with extreme sensitivity to even the slightest disturbances. orbiting at an altitude of merely about 6,000 kilometers, so close that it completes 3 orbits around Mars in the span of a single Martian day. Phobos resides well within what we call the rush limit. This boundary marks the point where tidal forces exerted by Mars overpower the Moon's own gravity, threatening its structural integrity. The only thing preventing Phobos from disintegrating in an instant is the internal strength of its rocky composition. Yet even that resilience is not infinite. Over millions of years, relentless tidal stresses have gradually eroded its structural stability, creating stress fractures and parallel grooves. Early signs that the Moon is already succumbing to Mars's gravitational grip, slowly being pulled apart grain by grain, orbit by orbit. It's a cosmic death by 1,000 cuts, a process that has been unfolding over the eons of planetary history. Now consider introducing Atlas into this precarious gravitational ballet. While the comet itself might not hold enough mass to exert a meaningful direct gravitational influence on Phobos, it carries something potentially far more dangerous: debris. As Atlas traverses the gravitational neighborhood of Mars, it could shed fragments and particles that drift into the orbital planes of the Martian moons. Even minuscule particles, when traveling at interstellar velocities, possess immense kinetic energy. A single grain of sand, impacting Phobos at 20 kilometers per second, would deliver an explosive force equivalent to a small nuclear device. Multiply this impact across thousands or millions of such particles, and the picture becomes terrifying. A seemingly gentle cosmic encounter transforming into a devastating bombardment. The cumulative effect of these impacts could be enough to push the already stressed structure of Phobos beyond its ultimate limit. Instead of a slow, millennia-long disintegration, the Moon could be catastrophically shattered during or shortly after Atlas's passage, unleashing a torrent of debris and fragments. What had been a slow-motion cosmic demolition, an orbiting time bomb, might suddenly explode into a cascade of chaos and destruction. But let us escalate this scenario further, to its most extreme and scientifically plausible conclusion. What if Atlas does not merely hasten Phobos's disintegration, but, in doing so, gives rise to an entirely new phenomenon in planetary science? What if the debris generated by this encounter becomes so voluminous and energetic that it forms Mars's first-ever ring system? The formation of planetary rings is a subject of complex physics, often misunderstood by the general public. Saturn's magnificent delicate rings are the product of a finely tuned dance between gravitational forces, particle collisions, and electromagnetic effects, all stabilizing over millions of years into a harmonious structure. In stark contrast, a ring formed from the violent fragmentation of Phobos, ripped apart by a cosmic impact, would not resemble Saturn's orderly bands of ice and rock. Instead, it would be an unstable, chaotic cloud of debris following wildly elliptical and unpredictable orbits around Mars. This new ring system would be a stark, tumultuous environment, an unsteady spectacle of fragments colliding, dispersing, and reforming on chaotic timescales, a far cry from the elegant, stable rings we observe around Saturn. It would mark a fundamental shift in the planetary architecture, transforming a serene celestial body into a tumultuous, debris-strewn landscape, an enduring legacy of a cosmic encounter that, in its worst form, could reshape Mars's very nature. Instead, Mars could find itself encircled by a chaotic maelstrom of debris, spiraling in wildly elliptical orbits that defy predictability. Some fragments would be massive enough to pose serious hazards to spacecraft, threatening to cause catastrophic damage to orbiting assets and future missions. Meanwhile, countless smaller particles, micrometeoroids, would fill the environment, creating a persistent shower that could gradually erode solar panels and damage optical instruments over time, rendering surface and orbital operations increasingly precarious. The challenge of navigating through such a hazardous field would turn into a nightmarish puzzle for mission planners, forcing them to contend with an environment far more hostile and unpredictable than anything previously experienced. Instead of designing trajectories around Mars's two small, predictable moons, future missions would have to account for thousands of fragments following chaotic and erratic paths. Trajectories that could shift unpredictably due to gravitational interactions and collisions. The risk of collision would escalate exponentially, transforming Mars's orbit into a perilous arena where routine spacecraft operations might no longer be feasible. The complex web of orbital debris would threaten to make Mars's vicinity too dangerous for sustained exploration or colonization. Orbital debris, however, follows the unforgiving laws of physics, a reality that complicates any cleanup efforts. Unlike terrestrial pollution, which can sometimes be mitigated through human intervention, space debris obeys the principles of conservation of momentum and collision physics. Every collision between fragments generates additional debris, often smaller and more numerous than before, each following its own unpredictable trajectory. This self-perpetuating cycle, known as the Kessler syndrome, can cascade into a runaway chain reaction, rendering vast swathes of Earth's orbital environment, and potentially Mars's, completely unusable for practical space activities. While concern over Kessler syndrome has long centered on Earth's crowded orbital lanes, Mars, with its weaker gravitational pull and thinner atmosphere, could be even more susceptible to such destructive cascades. The psychological toll of witnessing this fragmentation would be profound. Humanity's ambitions for Mars as a backup sanctuary, a new frontier for civilization, would be shattered in an instant. For decades, we have envisioned Mars as our second chance, an unspoiled bastion where humanity could build a sustainable future beyond Earth's confines. To see that hope disintegrate before our eyes, with debris clouds haunting its skies for centuries or even millennia, would be akin to witnessing the loss of our most cherished dreams of expansion, resilience, and renewal. The timeline for recovery from such an event could stretch to geological ages as planetary surfaces and atmospheres gradually rebuild, if they can at all. Following the relentless laws of celestial mechanics, fragments from the destruction of Phobos, or any debris generated by Atlas's chaos, could continue to threaten Mars's operations for thousands, perhaps millions of years, an enduring legacy of cosmic violence. Yet even this catastrophe would pale in comparison to a more insidious danger, the possibility that our focus is too narrow, too localized in assessing Atlas's true destructive potential. What if the October 3rd encounter was merely the first domino in a chain of gravitational perturbations, a cascade of orbital shifts that could, over time, threaten not only Mars but also our entire planetary system? The physics governing orbital dynamics operate on vast timescales that make human planning seem trivial. A seemingly insignificant gravitational nudge today might, decades or centuries from now, amplify into a significant destabilization, pushing celestial bodies onto collision courses or into destabilized orbits. As we prepare to consider this alarming chain reaction, we must face the disturbing possibility that Atlas's brief dance with Mars could set in motion a sequence of gravitational disturbances powerful enough to cascade through our solar system and ultimately threaten Earth itself. Such a scenario highlights how delicate and interconnected the celestial mechanics truly are, a fragile cosmic balance that could be perturbed with consequences that only reveal themselves over generations, long after the initial encounter has faded into history. Part 6. The Chain Reaction to Earth. In the vast expanse of space, distance can often create a false sense of security. Currently, projections from NASA indicate that Atlas will reach its closest proximity to Earth sometime in December of 2025, when it will be approximately 1.8 astronomical units away. To put that into perspective, that's roughly 270 million kilometers. An ostensibly safe buffer zone that should, under normal circumstances, shield our planet from any direct impact or catastrophic interference. However, in the interconnected cosmic dance of our solar system, such assumptions of safety are often illusory. The intricate web of gravitational influences means that even a seemingly minor event, like Atlas's approach, can set off a cascade of effects that ripple outward over extended periods, sometimes spanning decades or even longer. What occurs in October at Mars does not remain confined there. Instead, it propagates outward, subtly altering the delicate gravitational relationships that hold our solar system in balance. These ripples can gradually grow, influencing the orbits of planets, moons, and smaller objects alike. To understand the potential magnitude of these effects, we need to delve into the mathematics of orbital perturbation theory. Every gravitational encounter, no matter how slight, causes a tiny shift in the trajectory of involved objects. These shifts are measured in meters per second, seemingly insignificant when compared to the kilometers per second speeds of planets and asteroids. Yet these small changes are not trivial. They accumulate over time, especially through a phenomenon known as gravitational resonance. Just as a gentle push at the right moment can set a massive pendulum swinging with increasing amplitude, small orbital nudges can, through resonance, amplify over successive encounters. This process means that what begins as an imperceptible adjustment can, over multiple revolutions and gravitational interactions, grow into substantial shifts, measured in thousands of kilometers, altering the paths of celestial bodies in ways that are difficult to predict with certainty. One of the most immediate concerns arises from the possibility of debris generated during Atlas's close encounter with Mars. Particularly if fragmentation occurs, as we previously discussed. The fragments resulting from such an event would not simply fade away into the cosmic background. Instead, each piece would continue to follow its own modified orbit, influenced by the gravitational pulls of planets, the Sun, and other objects as it journeys through the inner solar system. This ongoing orbital evolution creates what astronomers often refer to as a persistent hazard environment. Some of these fragments might become caught in orbital resonances with Earth's orbit. Resonances occur when objects' orbital periods are in simple ratios with one another, leading to periodic gravitational nudges that can stabilize or destabilize their paths over time. This means that certain fragments could repeatedly pass through regions close to Earth, creating predictable but dangerous encounters that might last for decades, each pass increasing the potential risk. Other fragments, influenced by the chaotic nature of their post-fragmentation trajectories, could be perturbed into highly elliptical orbits, bringing them into the inner solar system during irregular, unpredictable time windows. The cumulative effect of these processes would be an increase in the background flux of potentially hazardous objects, small but persistent streams of debris that pose a long-term threat to Earth's safety. Despite significant advancements in planetary defense, the current detection systems are primarily calibrated to identify objects with relatively predictable orbits, asteroids and comets that follow well-understood paths within the context of our solar system. Recent years have seen remarkable progress in this area. The Asteroid Terrestrial Impact Last Alert System, commonly known as PAN-STARRS, along with upcoming projects like the Legacy Survey of Space and Time, are designed to give us years or even decades of warning before potentially dangerous objects make close approaches. These systems excel at tracking objects that follow known orbital patterns, allowing us to prepare deflection strategies or evacuation plans well in advance. However, the situation becomes far more complicated when it comes to the chaotic trajectories influenced by interstellar velocities and multiple gravitational encounters. Precisely the kind of paths that fragments from Atlas might follow after a fragmentation event. Such objects would not conform to the predictable profiles these detection systems rely on, making them far more difficult to identify and track accurately. Their approach angles, velocities, and compositions could all fall outside the parameters set by current algorithms, meaning that some hazardous fragments could enter Earth's neighborhood undetected or with insufficient warning. This gap in our planetary defense framework underscores a significant vulnerability. As our understanding and detection capabilities improve, so too must our strategies for recognizing and responding to the unpredictable chaos that interstellar objects can introduce into our cosmic environment. Their angles of approach could be anything but predictable, skewed and unusual from the standard paths astronomers are accustomed to tracking. Their velocities might be unexpectedly high or low, defying conventional models. Moreover, their compositions could be so different from typical asteroids, perhaps enriched with exotic interstellar materials, that they would confound our automated classification systems. These systems, designed to sort and analyze space debris based on familiar signatures, might be powerless against objects that don't conform to known categories. The threat posed by such fragments wouldn't necessarily unfold overnight. Instead, it could extend across generations, with consequences gradually building over decades. Unlike the immediate visceral drama of a collision, an impact creating a vast crater or an atmospheric shockwave, gravitational perturbations operate on what physicists call secular timescales. These are long, subtle shifts in orbital paths that accumulate imperceptibly at first but grow increasingly significant over extended periods, sometimes measured in decades, sometimes in centuries. The true danger lies in this slow, inexorable process, which can lead to chaos long after the initial encounter. We might not realize the full extent of Atlas's influence on Mars or Earth until the 2040s or even later, when orbital changes destabilize trajectories or new impact risks become undeniable. This lag in effect, this displacement of consequences across time, introduces a particularly insidious form of cosmic risk. Decision-makers today, politicians, space agency officials, planetary defense strategists, might be allocating resources and setting policies under the assumption that the situation is stable. Yet the fragments of Atlas, potentially composed of strange exotic materials, could be quietly drifting into more dangerous orbits, only becoming a threat many years down the line. The so-called Arkovsky effect, an intricate phenomenon, amplifies these concerns further, rendering long-term prediction nearly impossible. The Arkovsky effect occurs when small objects, tiny fragments of cosmic debris, absorb sunlight during the day and then re-radiate that heat during the night. This process produces a minuscule but persistent thrust, gradually nudging the object's orbits over time. While this effect is well understood in standard celestial mechanics, it assumes that objects have familiar thermal properties and behave predictably. But what if fragments of Atlas, forged from interstellar materials with thermal properties unlike anything in our solar system, respond in unexpected ways? Their orbits could evolve in ways that current models cannot accurately predict, potentially leading them onto collision courses with Earth or other planets. Imagine this nightmare scenario unfolding over the next 50 years. Initial simulations based on conventional asteroid behavior might classify these fragments as benign, harmless debris unlikely to threaten Earth. But unbeknownst to us, subtle forces like the Yarkovsky drift, an extension of the Arkovsky effect, could gradually push them into Earth-threatening orbits. By the time our telescopes detect a potential danger, the window for effective deflection or mitigation might have already narrowed to a point where intervention is impossible. History offers a precedent for such cascading gravitational disasters. The late heavy bombardment, roughly 4 billion years ago, is believed to have been triggered by a series of gravitational resonances among the outer planets. These resonances destabilize their orbits, unleashing a torrent of comets and asteroids into the inner solar system. A cosmic barrage that left scars on the moon and shaped planetary surfaces. Craters across lunar landscapes stand as silent witnesses to this chaos, a testament to how gravitational upheavals can transform peaceful celestial neighborhoods into shooting galleries. However, Atlas introduces variables that our ancient solar system never had to contend with. Objects traveling at interstellar velocities composed of exotic, unfamiliar materials and prone to fragmentation patterns that might not follow the familiar rules established over billions of years of solar system evolution. These factors could spawn a new category of gravitational cascade, one without any direct historical analog. Our models, built on the foundation of natural solar system processes, might be fundamentally inadequate in predicting or countering the unpredictable paths of these interstellar fragments. The implications for meteor showers alone are chilling. Earth routinely encounters streams of debris from known comets, famous annual meteor showers like the Perseids or Geminids, bright displays that thrill amateur astronomers and pose minimal threat. These showers consist of tiny particles, most of which burn up harmlessly in the atmosphere, occasionally causing satellite impacts. But if fragments of Atlas traveling at interstellar speeds and made of strange, unanticipated materials begin to intersect Earth's orbit, the consequences could be far more severe, ranging from powerful airbursts capable of devastating entire regions to a relentless increase in micrometeoroid hazards that threaten the safety of satellites, spacecraft, and even ground-based infrastructure. In essence, the cosmic neighborhood might become far more volatile and unpredictable than we've ever imagined, with the potential for cascading effects that could span generations. The slow, creeping influence of these fragments could quietly set the stage for a series of impacts or orbital shifts, culminating in a planetary crisis that no current technology or prediction models are prepared to. However, meteor showers originating from fragments of Atlas would constitute a phenomenon of a vastly different nature, unlike the familiar displays of the Perseids or Geminids, where minuscule particles incinerate harmlessly in our planet's atmosphere. These would be the harbingers of far more destructive events. Traveling at interstellar velocities, the fragments of Atlas, potentially composed of exotic materials that do not conform to the behavior of typical meteoroids, could trigger airburst phenomena comparable to the catastrophic Tunguska event of 1908. The Tunguska explosion, which razed approximately 2,000 square kilometers of Siberian forest, was caused by an object estimated to be only between 30 and 60 meters in diameter. Now envisage multiple Tunguska-sized impacts occurring in rapid succession, as Earth traverses streams of debris resulting from Atlas's fragmentation. The cumulative destructive power of such events could devastate entire continents over the course of decades. Our modern civilization's vulnerability to these cosmic phenomena has increased exponentially since that early 20th century calamity. Today, our interconnected power grids, global communication networks, and transportation systems create a web of cascade failure points that did not exist during Tunguska's time. A single high-altitude air burst over a densely populated metropolitan area could ignite a chain reaction of economic and societal disruptions, effects that might linger and ripple through the fabric of human society for many years, even decades. Recognizing these emerging risks, the insurance industry has already begun to grapple with the profound implications of increasing cosmic threats. Major players like Lloyd's of London and other leading insurers have been quietly developing models that attempt to quantify the potential damage from space weather events capable of disrupting global commerce. However, these assessments are based on the assumption that hazardous objects, such as fragments from Atlas, will be detected many years before they threaten Earth, providing sufficient warning to facilitate orderly evacuations and the fortification of critical infrastructure. In reality, the chaotic and unpredictable orbits of Atlas fragments could arrive with alarmingly short warning times, completely catching both emergency management agencies and financial markets unprepared. The economic toll of such sudden impacts could far surpass the initial physical damage, creating a death corridor of elevated cosmic risk that could persist for generations. What is perhaps most unsettling is the possibility that humanity is already committed to this cascade of events, regardless of what transpires on October 3rd. The gravitational perturbations that will ultimately influence Atlas's long-term trajectory and its influence on the inner solar system may have already been set into motion during earlier phases of its approach, even before the upcoming encounter. Orbital mechanics, as we understand them, are governed by a principle known as deterministic chaos. Systems where minuscule initial differences can lead to dramatically divergent outcomes, yet where these outcomes are ultimately inevitable once the initial conditions are in place. We may currently be experiencing the early stages of a gravitational cascade that was fundamentally predetermined when Atlas first entered our solar system months ago. The monitoring systems designed to provide early warning of such threats face their own vulnerabilities in this era of mounting cosmic chaos. Ground-based telescopes, despite their sophistication, can be hampered by atmospheric disturbances that obscure or distort observations. Space-based observatories engineered to detect and track debris are not immune to damage. Debris fields themselves can pose threats to their sensitive instrumentation, potentially compromising their ability to observe and analyze the very objects that could threaten us. Communication networks responsible for transmitting threat assessments to planetary defense systems could become overwhelmed or rendered ineffective by the electromagnetic upheaval detailed earlier in our discussion of Mars's atmospheric disturbances. Yet, even if our detection capabilities operate flawlessly, if we could identify every fragment of Atlas years or even decades before it poses a danger to Earth, the sobering truth remains that the technology required to redirect or mitigate such interstellar debris is still largely in the realm of theoretical science. The DART mission, a pioneering effort demonstrating that we can, under controlled conditions, alter the course of a known asteroid, offers some hope. However, its success hinged on precise knowledge of the target's composition, orbit, and predictable behavior, parameters that Atlas's fragments, with their mysterious interstellar origins and chaotic post-fragmentation trajectories, might not adhere to. This leaves us in a paradoxical position. We could be fully aware of a coming cosmic catastrophe, exactly when and where it will happen, yet remain powerless to prevent it. This is the core horror of the chain reaction scenario. It is not the immediate cataclysmic impact that terrifies us, but the slow, creeping deterioration of our cosmic environment, an unfolding catastrophe that stretches beyond the limits of human political and economic foresight. We might be witnessing the onset of humanity's first self-inflicted cosmic crisis, one triggered not by external forces alone, but by our own expansion into a solar system that, as it turns out, was never as stable as we once believed. Even as we grapple with these distant planetary-scale nightmares, we must confront the stark reality faced by our robotic emissaries orbiting Mars. These sophisticated spacecraft, our eyes, ears, and hands on the red planet, operate under engineering principles designed for a stable and predictable environment. They were built to withstand the typical hazards of space, not the unpredictable chaos that could ensue from an interstellar visitor's passage. What happens then when the most advanced space technology encounters forces that defy earthly rules? How resilient are our systems against an electromagnetic storm of cosmic proportions? This question brings us to the realm of Part 7, Spacecraft at Risk. Despite its often romanticized image in science fiction, space remains a hostile frontier. an environment that relentlessly challenges the fragile electronic systems humanity has developed to extend life and exploration beyond Earth's protective cocoon. Our spacecraft are marvels of precision engineering, delicate assemblies of sensors, processors, and communication modules, all designed to perform flawlessly in environments where even the tiniest failure can spell disaster. Orbiting Mars presents a set of unique challenges that push these machines to their operational limits. For instance, while the radiation environment around Mars is less intense than near Jupiter's magnetic maw, it still causes gradual degradation of electronic components over time, reducing their reliability. Micrometeoroid impacts, though statistically infrequent, can strike with surgical precision, disabling vital systems or disrupting operations just when we need them most. The planet's extreme temperature swings, plunging into the cold shadows of Martian night and then baking under unfiltered sunlight, introduce thermal stresses that slowly fatigue even the most robust materials and electronic circuits. The engineers who designed our current fleet of Mars orbiters, such as the Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, never envisioned operating in the chaotic electromagnetic environment that could result from Atlas's passage. Their systems were built with a different set of assumptions: stable space weather, predictable radiation, and manageable impacts. Yet should an interstellar visitor like Atlas trigger a massive electromagnetic storm, these spacecraft could find themselves vulnerable beyond their intended tolerances, facing conditions for which they were not designed. These spacecraft were meticulously engineered to observe Mars under its usual predictable conditions, not to withstand the chaos of cosmic-scale disasters. When considering the vulnerabilities ingrained in the architecture of modern space exploration vehicles, the risks become even more apparent. For instance, high-voltage power systems, crucial for powering advanced instruments and maintaining communication over the immense expanse of interplanetary space, can become dangerous liabilities if subjected to intense electromagnetic disturbances. Charged particle bombardments, such as those potentially emitted by Atlas's approach, can cause static electricity buildup. This accumulation can generate dangerous voltage differentials that arc across delicate circuit boards, resulting in immediate destruction of components that have taken years of development and testing to perfect. Take the Mars Reconnaissance Orbiter, launched in 2005, as an example. It houses some of the most sophisticated imaging and communication equipment ever sent to Mars. Its high-resolution camera is capable of resolving surface features smaller than a meter across, providing invaluable detail about the Martian terrain. Its radio science instruments probe the planet's atmosphere with an unprecedented level of detail, offering insights into its composition and dynamics. However, the orbiter's highly sensitive systems rely heavily on star trackers, precision optical sensors that keep the spacecraft properly oriented by observing fixed stellar positions. These sensors are vulnerable. A debris field resulting from Atlas's fragmentation could flood the sensors with unexpected light sources or generate false targets, rendering them useless. Without accurate attitude control, the spacecraft's high-gain antenna would be unable to maintain the precise orientation necessary to transmit data back to Earth. This would effectively sever the critical link that allows scientists to receive the orbiter's invaluable discoveries. Similarly, NASA's MAVEN mission, focused on studying how solar wind interacts with Mars's upper atmosphere, faces challenges of its own. MAVEN's instruments, including particle detectors and magnetometers, are calibrated to measure the gentle, steady flow of charged particles emitted by our Sun. But Atlas's passage could produce a flux of particles far beyond the instrument's designed capacity, possibly orders of magnitude higher, akin to trying to measure a gentle breeze during a hurricane. The sensors could become saturated or damaged permanently, losing their ability to provide reliable data. While the electromagnetic pulse effects ensuing from Atlas's approach are not quite like the fictional electromagnetic pulse weapons often depicted in Hollywood blockbusters, they could still induce damaging currents within spacecraft wiring systems. Given that modern spacecraft carry thousands of meters of electrical cables, acting like efficient antennas, they are particularly vulnerable. A sudden surge in ambient electromagnetic energy could turn these extensive wiring networks into conduits, channeling destructive currents that threaten the entire electrical infrastructure on board. Furthermore, each spacecraft's vulnerabilities are, in part, dictated by its mission-specific design choices. For example, the European Space Agency's Mars Express, which has been operating since 2004, has accumulated signs of age in several subsystems. Its hardware, already tested by years of operation in the harsh environment of space, may be less resilient to unexpected electromagnetic disturbances. The cumulative wear and tear over nearly 2 decades of service could exacerbate its susceptibility to damage from an intense electromagnetic event like the one Atlas might produce. In essence, these spacecraft, despite their technological marvels and years of meticulous engineering, are inherently fragile when faced with the unpredictable and violent forces of cosmic phenomena. Their reliance on precise optical sensors, delicate wiring, and robust yet limited power systems leaves them exposed to the full brunt of electromagnetic chaos. A chaos that, if unleashed by Atlas's approach, could disable or destroy some of humanity's most advanced tools for exploring and understanding the red planet. Components operating at the edge of their designed capabilities are particularly vulnerable when subjected to unforeseen, tumultuous electromagnetic disturbances. The latest addition to our Martian fleet, the Trace Gas Orbiter, exemplifies this delicate balance. Equipped with cutting-edge spectrometers, it is meticulously designed to detect minute concentrations of trace gases within the Martian atmosphere, including potential biosignatures that could hint at microbial life, past or present. These highly sensitive instruments demand an environment of extraordinary stability. Any fluctuation in electromagnetic conditions risks overwhelming their measurements with spurious signals, rendering months or even years of carefully gathered data scientifically meaningless. Even more concerning is the potential for electromagnetic interference to damage the spectrometer's delicate calibration systems. Such damage would necessitate intricate recalibration procedures, complex adjustments that might be impossible to perform remotely in the aftermath of a disruptive event. To understand the full scope of the danger, let's project this scenario to its most disastrous extreme. What if Atlas's passage through the inner solar system doesn't merely threaten individual spacecraft, but sets off a chain reaction of systemic failures across the entire orbital infrastructure around Mars? Imagine a scenario where the electromagnetic chaos generated by Atlas's erratic coma and debris shed is so severe that it triggers widespread electronic disturbances. These disturbances could activate a cascade of emergency shutdown protocols, a phenomenon known as safe mode, effectively rendering our robotic assets blind and deaf in the Martian orbit. Spacecraft are designed with safe mode systems precisely for these eventualities. When sensors detect anomalies, the spacecraft automatically power down non-essential systems, reorient solar panels toward the sun to maximize power, and await further instructions from Earth to diagnose and recover. However, safe mode operates under the critical assumption that the disruptive conditions are temporary, conditions that ground controllers can eventually diagnose and correct. But if the electromagnetic disturbances from Atlas persist for weeks or months, our orbiters could remain trapped in this dormant state indefinitely. During this prolonged silence, they would be unable to perform scientific observations, unable to relay vital data from surface rovers, and entirely cut off from human command and control. The psychological and strategic repercussions of such a scenario would be profound. The public and scientific community alike would react with alarm at the simultaneous loss of all orbital communication assets. News outlets and social media platforms would be inundated with conspiracy theories, speculations of cosmic calamities, cover-ups, or even attempts at deliberate sabotage. Fueling fears that our technological civilization's reach into Mars has been irrevocably compromised. The carefully cultivated global support for Mars exploration, built through decades of successful missions and breathtaking imagery, could evaporate overnight, replaced by panic and skepticism. Space agency mission controllers, especially those at JPL and other international partners, would face an unprecedented challenge. How to manage a crisis where the very systems meant to safeguard our robotic explorers are rendered useless. Traditional recovery protocols rely on the ability to communicate with affected spacecraft, to run diagnostics, and to upload corrective commands remotely. But if electromagnetic interference renders these communications unreliable or altogether impossible, mission teams might find themselves helpless, stranded, unable to diagnose or resolve issues from afar. In essence, the very infrastructure designed to ensure the resilience of our robotic explorers could become a liability, an unintentional catalyst for a broader systemic failure. The implications extend beyond mere operational setbacks. They threaten the continuity of our scientific endeavors and our understanding of Mars itself. The chain reaction of electromagnetic disturbances initiated by Atlas's passage would not be confined solely to Mars, but would ripple outward, profoundly affecting surface operations as well. The Perseverance and Curiosity rovers, two of our most advanced robotic explorers on Mars, heavily rely on orbital relay satellites to sustain their vital communications with Earth. These relay assets act as essential intermediaries, transmitting data and receiving commands in a seamless flow. Without these crucial systems functioning properly, the rovers would be forced to communicate directly with Earth using their own low-power radio transmitters, a process that dramatically hampers data transfer rates and severely restricts operational flexibility. Such limitations could mean slower decision-making, reduced scientific productivity, and an increased vulnerability to unforeseen hazards on the Martian surface. What makes this scenario even more concerning is the potential for Atlas to trigger a rare and perilous coupling with solar space weather, an event long forewarned by space physicists, but yet to be observed in practice. If Atlas's approach coincides with a period of heightened solar activity, such as a major solar energetic particle event or a colossal coronal mass ejection, the combined effects could overwhelm spacecraft shielding designed to withstand individual threats. These protective systems are calibrated to handle isolated incidents, but the simultaneous onslaught of cosmic debris and intense solar radiation could surpass their limits, leading to widespread failures. The aftermath of such a cascade of failures would extend over years, not days, unlike terrestrial infrastructure, which can often be repaired by deploying technicians or machinery directly to the site. Space-based assets require intricate troubleshooting procedures conducted across the vast expanse of interplanetary space, with communication delays spanning several minutes. These delays complicate real-time problem-solving and could hinder timely responses to emerging threats. Some spacecraft, battered by electrical surges or prolonged exposure to charged particles, might suffer irreparable damage, their electronic components degraded beyond recovery. Components that have functioned reliably for decades could suddenly cease to operate, not because of natural wear and tear, but due to abrupt cosmic-level forces that push their design parameters past the breaking point. The loss of our Mars orbital network would represent a significant setback, delaying scientific progress by years or even decades. Critical investigations into Mars's climate history, atmospheric composition, and geological processes, research that was just beginning to yield transformative insights, would be interrupted or halted altogether. Yet perhaps the gravest consequence of such a failure would be our inability to observe or comprehend what Atlas truly does to the red planet itself. We might be aware that something momentous happened at Mars, perhaps a significant impact or atmospheric disturbance, but we would remain in the dark about the full scope of its effects until new missions could be developed, constructed, and launched. A process that often takes a decade or more. While contemplating these technological nightmares, it's vital to recognize that Atlas's influence extends beyond immediate spacecraft systems into the broader realm of solar system dynamics. Our Sun, despite its apparent steadiness to casual observers, functions as a delicate fusion reactor teetering on the brink of explosive instability. Dramatic cosmic events, such as Atlas's close approach, could have ripple effects that influence solar activity itself. What if the October 3rd encounter is not merely a localized threat to Mars and its satellites, but the precursor to a solar weather catastrophe that impacts every planet within our cosmic neighborhood? This leads us into the realm of radiation storms and solar chaos. The Sun, for all its outward appearance of stability, operates as a finely balanced system of nuclear fusion, an unimaginably hot and energetic process maintained in a fragile equilibrium. It is a barely controlled fusion reactor, perched on the edge between steady stellar emission and catastrophic eruptions. Solar activity follows roughly 11-year cycles characterized by periods of relative calm, punctuated by intense bursts of electromagnetic energy, which can unleash solar storms capable of disrupting technology across the entire solar system. These solar outbursts generate a torrent of charged particles, magnetic disturbances, and energetic radiation that can impact satellites, power grids, and biological systems on Earth and beyond. The danger arises when Atlas's passage, which already involves the release of a vast coma of ionized gases and possibly debris, coincides with a period of maximum solar activity, an era when the Sun's magnetic field is already destabilized and primed for explosive release. If the comet's approach triggers a coupling with the Sun's magnetic environment, perhaps through complex interactions between its ion tail and the solar wind, the resulting effects could be far more severe than any single event alone. The combined influence could catalyze a large-scale solar energetic particle event, or a major coronal mass ejection, overwhelming the protective shielding of spacecraft and satellites designed to withstand more modest storms. Such an event could initiate a chain reaction that persists for months or even years, disrupting communication networks, navigation systems, power grids, and climate systems on Earth and other planets. The Sun's magnetic field, which governs space weather, might become increasingly unstable, leading to a prolonged period of heightened solar activity, what scientists have long feared but have yet to observe at such a scale. This underscores the interconnectedness of cosmic phenomena. A relatively small intersolar activity operates on an approximately 11-year cycle, during which the Sun can unleash powerful electromagnetic storms capable of disrupting technological systems across the entire expanse of our solar system. These natural solar outbursts, while formidable, are well-understood phenomena that have occurred repeatedly over millennia. Yet they pale in comparison to the potential chaos that could unfold if the passage of Atlas through the inner solar system coincides precisely with the Sun's most active phase. Atlas's perihelion, the point at which it ventures closest to our star, will occur in late October of the year 2025, when it will be approximately 1.4 astronomical units from the Sun. To put that into perspective, this distance places Atlas comfortably outside the realm of the solar flares or sun grazes that sometimes plunge directly into the Sun's glowing corona, causing spectacular solar eruptions. However, it situates the comet well within a zone where the interactions between solar wind and cometary material could become immensely intense and highly unpredictable. Under normal circumstances, the physics governing a comet's interaction with solar wind follow well-established principles. As it approaches the sun, solar radiation heats and vaporizes the comet's surface materials, creating a luminous cloud known as the coma, and forming a tail that always points away from the sun, an iconic feature that has inspired human imagination for countless generations. The solar wind, a relentless stream of charged particles traveling outward from the sun at speeds exceeding 400 kilometers per second, sculpts this tail into a distinctive shape that points anti-sunward. This process is well documented and predictable, forming the basis of our understanding of cometary behavior. Yet Atlas is not a typical comet operating under usual conditions. Its enormous carbon dioxide coma and its erratic variations in brightness strongly suggest the presence of internal processes and chemical reactions that defy our standard models. The irregularities observed, such as sudden surges in luminosity and atypical tail formations, imply that its behavior is influenced by complex internal dynamics, possibly involving exotic chemical interactions or structural instabilities that we have yet to fully comprehend. Now consider what might happen when such an anomalous object with unconventional patterns of activity ventures into the sun's complex electromagnetic environment. The comet's extended tail of electrically charged particles propelled and accelerated by the solar wind can stretch millions of kilometers into space during perihelion. This tail isn't merely a passive stream. It actively interacts with the solar wind, the sun's magnetic field, and the broader electromagnetic tapestry woven throughout the solar system. These interactions could, in some circumstances, generate feedback loops, regions where the comet's plasma emissions influence and are influenced by the sun's magnetic activity. The sun's magnetic field lines, which extend far beyond its surface, form intricate and dynamic patterns that are still only partially understood by solar physicists. When a massive electrically charged tail from Atlas crosses these magnetic field lines, it could theoretically induce perturbations that travel back toward the sun's core. Such disturbances might serve as triggers for increased solar activity, potentially igniting solar flares or coronal mass ejections in regions that would otherwise remain relatively quiet. This scenario introduces a disturbing possibility that a relatively small interstellar object could influence or even destabilize the sun's magnetic environment in ways that amplify solar storms. The stakes become especially dire if this comet's perihelion passage occurs during a period when the sun is already nearing the peak of its natural 11-year cycle, when magnetic fields are most unstable and energy is primed for rapid release. In this case, the electromagnetic perturbations emanating from Atlas's extended tail could arrive just as the sun's magnetic field lines are on the verge of a catastrophic reconfiguration. The result could be a solar energetic particle event of unprecedented magnitude, an outburst of solar radiation and charged particles that dwarfs the infamous Carrington event of 1859, which, in its time, was the most intense solar storm recorded. Such an extraordinary storm could unleash a cosmic tempest of a scale never before seen, capable of disrupting satellite communications, knocking out power grids and damaging space-based technology across the entire solar system. It would be a storm that makes the Carrington event seem like a gentle spring shower by comparison, potentially inducing widespread blackouts, communication failures, and cascading technological failures that could last for weeks or months. The implications for our modern civilization, so heavily dependent on reliable space-based infrastructure, would be profound, with the potential to plunge society into chaos reminiscent of the dark days before the dawn of the electrical age. The Carrington event, a solar storm caused by a relatively modest coronal mass ejection, once demonstrated the immense power of our sun's natural fury. In the mid-19th century, this event was capable of disrupting telegraph systems across North America and Europe, with sparks flying and sparks visible as far south as the Caribbean. At that time, human civilization's reliance on electricity was minimal. Most systems were primitive and localized. However, a similar solar storm today, especially if intensified by an interstellar influence such as Atlas, would be cataclysmic on an entirely different scale. Power grids across continents would likely go dark, satellite networks would be rendered useless, and communication infrastructures vital for everything from commerce to emergency response would grind to a halt. The economic toll would be staggering, measured in trillions of dollars, and the global recovery could take years, if not decades. Now imagine an Atlas-enhanced solar storm, one that surpasses anything we've experienced before. The charged particles accelerated by such an event would flood toward Earth at a significant fraction of the speed of light. Their energy so immense that they could overwhelm even the most robust satellite shielding designed for normal space weather. These particles could penetrate protective layers, causing widespread damage to spacecraft electronics and terrestrial power systems alike. Our space weather monitoring systems, such as the Solar and Heliospheric Observatory, SOHO, the Geostationary Operational Environmental Satellites, GOES, and the Deep Space Climate Observatory, DSCOVR, would themselves be at grave risk. These instruments are crucial for early warning, detecting solar activity long before it reaches Earth. But the very phenomena they are meant to observe, massive electromagnetic outbursts and particle streams, could destroy or impair them in the process. If these early warning systems are compromised or obliterated by the initial barrage of comet-driven charged particles, subsequent waves could strike Earth with little or no forewarning. The cascading effects on our modern civilization would be unprecedented and catastrophic, far beyond any event recorded in human history. Global navigation systems such as GPS rely on precise timing signals from orbiting satellites. If these satellites lose synchronization or are disabled, navigation and timing services would collapse, crippling everything from military operations to everyday GPS-guided transportation. The entire backbone of the Internet, dependent on perfectly synchronized data flow, would fragment, causing widespread disruptions in communication, commerce, and financial transactions. Air traffic control systems, which depend on radar and radio signals, would revert to visual flight rules, increasing the risk of accidents and chaos in the skies. But Earth would not be the only planet under threat. Mars, already teetering on the brink of chaos from Atlas's passage, would face an onslaught of charged particles capable of stripping away large portions of its already fragile atmosphere. The radiation levels at the Martian surface would skyrocket to lethal thresholds, endangering any human explorers or robotic missions present at the time. The moons of Jupiter and Saturn, such as Europa and Enceladus, usually shielded by their massive planets' magnetic fields, could still suffer from intense radiation doses. These doses could sterilize their surfaces or penetrate several meters deep, potentially destroying any microbial life that might exist beneath the icy crusts. Such radiation bombardment could also interfere with the delicate subsurface oceans believed to harbor extraterrestrial life, effectively sterilizing these environments and ending any possibility of biological activity there. Perhaps most unsettling is the prospect that an Atlas-triggered solar storm might not simply be a transient event. Instead, it could set off a feedback loop, an electromagnetic and particle cascade, that persists long after Atlas has departed the inner solar system. This self-sustaining cycle could maintain an environment of extreme and unpredictable space weather, continuously battering planets and their atmospheres and inducing long-lasting chaos. The very fabric of our solar system's electromagnetic environment could be fundamentally altered, with consequences rippling across planets, moons, and space-based infrastructure for decades or even centuries, to the point where the idea of stable, predictable space weather becomes a thing of the past. The disruptions to our star's magnetic shield caused by Atlas could linger for months or even years, preventing the solar magnetic field from returning to its stable state. During this uncertain period, our sun might continue unleashing intensified bursts of energetic particles, solar winds, solar energetic particles, and magnetic disturbances that pose a persistent threat to technological civilizations scattered across multiple planets. Our existing knowledge and historical records offer scant guidance for managing such a scenario because during the era of space-age technology, no comparable event has ever been documented or experienced. The most comprehensive data we have on solar storms stems from ice core samples drilled from Earth's polar regions and from tree ring studies, natural archives that record episodes of heightened solar activity over millennia. These records reveal that Earth's sun has periodically entered phases of increased activity, marked by intense solar winds and magnetic storms. However, they do not provide detailed insights into the specific mechanisms, durations, or sudden intensifications that might occur during an event amplified by an interstellar visitor like Atlas. Current space weather prediction models, complex simulations that incorporate solar physics, magnetic field interactions, and particle fluxes, were primarily designed to account for solar phenomena driven by internal solar dynamics and known solar cycles. They were not intended to accommodate the additional variables introduced by an interstellar comet's interaction with the sun's magnetic field. As a result, these models might prove entirely inadequate when trying to forecast the behavior of a solar storm intensified by Atlas's influence, an event that could defy our existing understanding and preparedness. The policy implications of such an event would be staggering and multifaceted. How can we prepare a modern civilization so heavily reliant on fragile electromagnetic infrastructure for a phenomenon that might materialize suddenly, with little warning, and last for an extended period? How do we ensure the continuity of emergency services which depend on reliable communication systems and satellite networks, when those very systems could be among the first casualties of electromagnetic chaos? How do we prevent societal chaos and economic collapse when the just-in-time supply chains, financial transactions, navigation systems, and communication networks, each intricately woven into our daily lives, are vulnerable to simultaneous failure? International cooperation would become absolutely essential in managing a planetary-scale space weather catastrophe. Yet paradoxically, the same electromagnetic chaos that threatens our technological backbone could also disable the very communication networks, such as satellite links, global navigation systems, and intergovernmental communication channels, that are critical for coordinated response efforts. This dual threat could leave humanity facing a planetary emergency, while being unable to effectively organize or implement mitigation strategies, amplifying fear, confusion, and disorder. Even as we grapple with these electromagnetic nightmares, it's vital to remember that Atlas's influence might extend beyond just charged particles and magnetic disturbances. Suppose the comet's passage does not merely disrupt our technology but also fundamentally alters the chemical environments of planetary surfaces and atmospheres. What if its passage triggers subtle chemical reactions, introduces exotic compounds, or changes the atmospheric composition in ways that influence a planet's long-term habitability? Could Atlas's legacy be measured not only by immediate impacts or electromagnetic chaos, but also by slow, insidious chemical modifications that accumulate over decades? Modifications that might either hinder or unwittingly facilitate planetary transformation. This leads us into the realm of planetary terraforming, not through deliberate engineering but as a byproduct of cosmic accident. The idea of transforming Mars from a barren, frigid world into a hospitable environment suitable for human life has long captivated the scientific community and science fiction enthusiasts alike. Most terraforming proposals involve carefully controlled incremental processes that unfold over centuries, involving releasing greenhouse gases to thicken the atmosphere, melting polar ice caps to create liquid water bodies, and introducing extremophile organisms to establish resilient biological cycles. But what if Atlas, through its cosmic journey and interaction with the solar system, inadvertently accomplishes a form of planetary terraforming, not by human design but as a consequence of its passage? Instead of a gradual, predictable process, the comet might trigger rapid, chaotic environmental changes, altering atmospheric chemistry, modifying surface compositions, and disturbing climate systems in ways never anticipated. In this cosmic accident, the comet's immense coma, rich in exotic ices and organic compounds, could inject vast quantities of greenhouse gases like carbon dioxide or other more complex molecules into planetary atmospheres. These chemical contributions could catalyze runaway greenhouse effects or atmospheric instability, transforming planetary environments in a matter of years rather than centuries. In essence, Atlas's cosmic arrival might serve as an unintentional agent of planetary change, forcing us to reconsider the boundaries between natural planetary evolution and cosmic accident. While traditional planetary science views terraforming as a slow, deliberate process, an ambitious yet controlled effort, Atlas could be acting as a natural, albeit unpredictable catalyst, dramatically accelerating environmental transformations. In this cosmic scenario, a comet from another star system becomes an agent of planetary modification, reshaping worlds not through engineering, but through chance chemical and atmospheric upheavals. What if, instead of a slow, controlled, and ultimately beneficial transformation, like the carefully planned terraforming processes envisioned by scientists, we are witnessing a swift, tumultuous upheaval that renders Mars even less hospitable to human life than it is today? The colossal release of carbon dioxide from Atlas's coma signifies a chemical payload of incomprehensible magnitude. Spectroscopic observations indicate that the comet is venting CO2 at rates that eclipse anything previously documented within our entire solar system. While most of this gas will likely miss Mars altogether, dispersing into the interplanetary void, even a tiny fraction of it could amount to millions of tons of additional greenhouse gases slipping into the Martian environment. Under ordinary circumstances, such an influx might seem advantageous, an unintentional head start for terraforming efforts, since carbon dioxide is the primary greenhouse gas targeted in most proposals to thicken Mars's atmosphere and increase surface temperatures. After all, more CO2 could accelerate the warming process necessary to make the planet more amenable to future colonization. Yet the devil is always in the details. The delicate chemistry of planetary atmospheres is a complex dance, and an unanticipated surge of gases, especially one as chaotic as this, could trigger cascading reactions with unpredictable and potentially catastrophic consequences. Mars's existing atmospheric system has endured and remained relatively stable for millions of years, maintained in a fragile equilibrium. A sudden chemical input, regardless of whether the gases are already present or not, can upset this balance, initiating a chain reaction of destabilization that spirals beyond control. Unlike the slow, methodical release envisioned in terraforming strategies, Atlas's carbon dioxide isn't arriving as a measured, controlled infusion. Instead, it is being delivered in a chaotic, sudden surge, coinciding with electromagnetic disruptions, possible impacts from debris and dust storms, each of which could alter how this greenhouse gas interacts with and transforms the existing atmospheric chemistry. Consider the albedo effects alone. Mars's characteristic reddish hue, primarily due to iron oxide dust, reflects sunlight in specific ways that help regulate its surface temperature. However, Atlas's passage might deposit vast quantities of dark, organic-rich dust across extensive regions of the planet's surface. Composed of materials formed in alien stellar environments, this dust could have thermal absorption properties entirely different from those of Mars's native soil. Darker surfaces absorb more sunlight, converting it into heat more efficiently. This principle, simple yet profound, could set off a runaway heating process, local temperature spikes that vaporize subsurface ice, releasing additional water vapor into an atmosphere already teetering on the brink of instability. This additional moisture would not exist in isolation. It could interact with the influx of carbon dioxide in ways that produce acid rain, further altering surface chemistry and potentially damaging nascent biological or ecological processes. But the scenario grows even more terrifying when considering the planetary scale implications. What if Atlas's chemical contributions do not merely nudge Mars toward a more Earth-like climate? What if they push the entire planetary environment into a Venus-like greenhouse hell? An unbounded runaway effect that transforms the red planet into an inferno? Venus, despite its similarities in size and bulk, is a world transformed by a catastrophic greenhouse effect that has made its surface hotter than melting lead, crushing all hopes of terraforming without extraordinary intervention. Its thick, carbon dioxide-laden atmosphere traps heat with such ferocity that even the most advanced spacecraft would be instantly endangered. The planet's surface conditions are so extreme that they have thwarted efforts to explore and understand it fully. If Atlas's chemical emissions, delivered in a sudden chaotic burst, interact with Mars's environment in ways that amplify greenhouse warming, the red planet could rapidly evolve into a hellscape resembling Venus, with surface temperatures soaring far beyond the thresholds of human survivability. This nightmare scenario underscores a fundamental truth. Planetary atmospheres are extraordinarily sensitive systems. Even seemingly minor inputs like a sudden burst of CO2 can, under the right conditions, ignite a chain of reactions that spiral out of human control. The implications are staggering, not only for Mars's future but for planetary engineering and our understanding of climate stability across worlds. The risks of such an outcome are compounded by the unpredictable interplay of dust, heat absorption, water vapor, and chemical reactions, each capable of transforming Mars into something far more hostile than we ever anticipated. Mars, with its lighter gravitational pull and its greater distance from the Sun compared to Earth, should, under normal conditions, be relatively resistant to the kind of runaway greenhouse effect that transformed Venus into a scorching hellscape. Typical planetary models suggest that Mars's atmosphere, composed primarily of carbon dioxide, would require extraordinary circumstances to spiral beyond control. However, the arrival of Atlas introduces variables that have never before been integrated into our planetary climate simulations. Among these are exotic organic compounds originating from interstellar space, which could act as catalysts, sparking chemical reactions that dramatically amplify greenhouse warming, much more than what pure carbon dioxide alone could induce. Two critical factors hint at the potential for rapid climate transformation: the timeline and the thresholds. Instead of unfolding over millions of years as natural climate shifts tend to do, such processes could accelerate to occur within a matter of years or decades. When a planetary atmosphere is pushed beyond certain critical thresholds, it can undergo swift and irreversible changes, fundamentally transforming its character in a surprisingly short span of time. What might start as a modest enhancement to Mars's existing greenhouse effect could snowball into a runaway scenario, leading to a complete and permanent alteration of the atmosphere. This possibility has profound implications for future missions to Mars, which are currently being planned under the assumption that the planet's environment will largely remain stable and predictable. These missions, based on models of Mars's current atmospheric conditions, could find themselves confronting conditions that bear no resemblance to the scenarios they prepared for. Life support systems, engineered to operate in the known chemical and atmospheric environment of Mars, might catastrophically fail when faced with the new, altered chemistry left behind by Atlas's passage. In situ resource utilization, or ISRU, remains a cornerstone of long-term Mars habitation plans. This technology relies heavily on extracting water, oxygen, and even rocket fuel from the Martian environment through well-understood chemical processes. But if Atlas's arrival fundamentally alters the planet's chemical inventory, introducing unfamiliar organic compounds, catalysts, or reactive substances, these ISRU systems could become not only useless but potentially dangerous. Imagine astronauts arriving in the year 2030, only to discover that the atmospheric processing units they relied on now produce toxic gases instead of breathable air, or that their water extraction systems are contaminated with organic pollutants, making the water unsafe despite purification efforts. The psychological toll of such a revelation would be severe. Humanity's dreams of establishing a foothold on Mars rest on the hope of an environment that, while harsh, is nonetheless manageable. Mars has long been viewed as our best backup plan, a safeguard against catastrophic events on Earth that could wipe out human civilization. To find that an interstellar visitor has rendered this crucial step impossible, right when we are finally reaching the technological maturity needed for long-term colonization, would be akin to watching our species' prospects for survival evaporate in real time. Such a scenario would undermine centuries of planning, investment, and hope for a multi-planetary future. But the changes prompted by Atlas might not be limited solely to the surface chemistry or even the atmosphere. The comet's passage could also significantly alter Mars's electromagnetic environment, creating ripple effects that influence everything from auroras to the behavior of dust storms. Mars's weak magnetic field offers minimal protection against charged particles streaming through space, making the planet particularly vulnerable to changes in the local space weather. Any shift in this delicate electromagnetic shield could lead to increased auroral activity, more intense and widespread than the faint displays currently observed, and could influence the dynamics of dust storms, potentially making them more frequent or more severe. Mars's susceptibility to charged particles is a direct consequence of its feeble magnetic defenses. Without a strong magnetic field, the planet's surface and atmosphere are exposed to the full brunt of solar and cosmic radiation. If Atlas's passage disturbs the surrounding space environment, either by shedding charged organic compounds or by inducing electromagnetic fluctuations, Mars's atmosphere and surface could be subjected to heightened activity. This heightened sensitivity would make the planet even more vulnerable to the influence of space weather, with unpredictable consequences for its climate, its potential habitability, and future human explorations. The electromagnetic disturbances stemming from Atlas's passage could profoundly disrupt the delicate ionosphere of Mars, leading to interference with radio communications that might persist for decades. Such disruptions could fundamentally alter the operational landscape for future missions to the Red Planet, compelling scientists and engineers to develop entirely new communication technologies. Approaches vastly different from those currently in progress. The dependable communication windows that mission planners have long relied upon could become irregular, sporadic, and unpredictable, complicating coordination, data transfer, and real-time decision-making. Beyond communication challenges, the implications of enhanced dust storms, potentially intensified or made more frequent by Atlas's electromagnetic influence, could reshape the entire strategy of Mars exploration for generations. If these effects trigger more intense or persistent dust storms, the solar power systems that most current missions depend upon might become unreliable, threatening the very backbone of sustainable operations on Mars. Under such circumstances, reliance on nuclear power sources, currently considered optional or supplementary, might shift into a necessity for any long-term presence or colonization efforts, ensuring survival amidst an increasingly hostile environment. Perhaps most unsettling of all is the troubling possibility that we may not fully grasp the extent of Atlas's impact on Mars until many decades have passed following the October 3rd encounter. The processes of atmospheric chemistry and environmental change operate on complex, often slow, timescales that can make immediate assessment impossible. Chemical reactions or atmospheric alterations initiated by Atlas's passage could continue quietly evolving over years, only revealing their true impact once future missions attempt to operate in altered conditions. This gradual shift could catch us unprepared, revealing a transformed Mars that no longer resembles the environment we once understood. This leads us into a sobering reflection on planetary engineering and terraforming efforts. The scenario underscores a fundamental gap in our understanding. We lack comprehensive knowledge of planetary atmospheres' responses to sudden, large-scale chemical inputs. While our models are reasonably accurate for predicting slow geological changes over millions of years, they have never been tested against the kind of cosmic chemical shock that Atlas might produce. The potential for a planetary environment to spiral into unpredictable states following such an event emphasizes the limits of our current predictive capabilities. Yet even amidst these environmental nightmares, the most insidious threat might not be physical devastation at all. What if the encounter proceeds exactly as official models predict? No impact, no electromagnetic chaos, no chemical catastrophe. Yet society refuses to accept that nothing extraordinary occurred. What if the true danger lies not in the physical realm but in the realm of information? This brings us to what can be called the "don't look up" angle, a reflection on the modern flow of information in the digital age. In today's interconnected world, information propagates through complex, often chaotic channels that can be more unpredictable and more dangerous than the movements of celestial bodies. When a significant astronomical event takes place, the chasm between scientific understanding and public perception can widen rapidly, transforming rational discourse into a battleground of misinformation and fear. Atlas's October 3rd encounter with Mars offers a perfect storm of conditions ripe for an informational catastrophe. The event coincides with a solar conjunction period during which Earth-based observations are inherently limited. The data collected requires weeks or even months of detailed analysis before meaningful conclusions can be confidently drawn. Meanwhile, the behavior of an interstellar object, whose trajectory and characteristics defy established patterns, serves as a cosmic wildcard, fueling speculation far more easily than providing definitive answers. The unknown nature of Atlas's behavior, combined with the delays in data interpretation, creates fertile ground for misinformation, social panic, and conspiracy theories to flourish. In this scenario, the real catastrophe might not be in the physical changes to Mars, but in how information, or misinformation, shapes collective understanding. The danger is that society could dismiss the absence of dramatic impacts or electromagnetic chaos as a cover-up, or simply refuse to believe that the encounter was benign. The result could be a widespread loss of trust in scientific institutions, fueling fear and chaos that ripple through political, social, and technological systems. This informational cascade could undermine efforts to prepare for, mitigate, or understand the true nature of cosmic events, leaving humanity vulnerable not just to interstellar threats, but to the destabilizing power of misinformation itself. In essence, this angle highlights a profound truth. In the modern age, the dissemination and perception of information are as crucial, if not more so, than the physical phenomena themselves. The October 3rd encounter with Atlas exemplifies how the limits of our observational and analytical capacities combined with the rapid spread of unverified claims, could turn what might be a minor cosmic event into a global crisis of understanding and trust. NASA and the European Space Agency have approached the public discourse surrounding ATLAS with remarkable restraint and precision. Their official statements, carefully crafted and measured, openly acknowledge the object's peculiar and unprecedented nature, confirming that comprehensive observational campaigns are underway to study it. Yet these agencies deliberately refrain from issuing the kind of sensational imagery or speculative narratives that tend to capture the imagination of the general public. While this prudence is rooted in sound scientific judgment, it inadvertently creates a void, an information vacuum, where ambiguity and uncertainty flourish. In this absence of dramatic visuals or definitive explanations, alternative stories and interpretations quickly take root. Social media algorithms designed primarily to maximize user engagement rather than promote factual accuracy amplify the most sensational and alarming interpretations of the incomplete data available. What begins as cautious scientific communication eventually becomes a fertile ground for misinformation and fear-mongering, as the most dramatic narratives overshadow the nuanced reality. By the time the official scientific analyses, such as those from the James Webb Space Telescope, are thoroughly reviewed and made public, public opinion may already be deeply influenced by false or exaggerated claims. Misinformation can solidify into a dominant narrative, making it exceedingly difficult for factual corrections or scientific clarifications to gain traction. This pattern echoes the recent history of astronomical misinformation campaigns, which have illustrated how swiftly speculative stories can outpace verified information when phenomena challenge our conventional understanding. The 2021 uncovering of unidentified aerial phenomena, UAP, by the United States government exemplifies this phenomenon vividly. Official disclosures, intended to foster transparency, instead ignited a firestorm of speculation that outstripped authoritative explanations. Congressional hearings meant to clarify and inform ended up generating more questions than answers, fueling conspiracy theories and alternative narratives rather than dispelling them. ATLAS presents an even more intricate challenge because the object itself is genuinely anomalous. Its properties and behaviors defy straightforward explanation. Its enormous carbon dioxide coma, the erratic fluctuations in brightness, and its exotic orbital characteristics all contribute to a core of real mystery. These elements provide ample material for speculation, making even the most outlandish theories seem plausible to those without deep expertise. Adding to the complexity is the delayed schedule for scientific data release. The infrared observations of ATLAS made by the James Webb Space Telescope shortly after the encounter in August are still under detailed analysis. These results are subject to peer review and verification processes that prioritize accuracy and thoroughness over speed. As a result, meaningful data might not reach the public for months, possibly even longer, after the October 3rd event. During this waiting period, unchecked speculation continues to circulate, operating without the constraints of verified facts. Meanwhile, amateur astronomers and citizen science groups are conducting their own observations. Equipped with increasingly sophisticated backyard telescopes and imaging tools, they share their findings instantly on social media. However, their images and measurements, while impressive in their own right, often lack the calibration and sensitivity of professional observatories. Artifacts, misinterpretations, or artifacts, common in amateur data, may be mistaken for significant phenomena. These images, rapidly disseminated and widely circulated, can be compelling to the untrained eye and to the general audience, further fueling the "don't look up" scenario. This confluence of factors, deliberate scientific restraint, rapid dissemination of amateur data, and the algorithms that favor sensationalism, sets the stage for a dangerous scenario. It fosters a cultural environment where the public, influenced by incomplete or misinterpreted data, might believe that a catastrophic event has occurred on Mars, regardless of the actual facts. Even minor anomalies, natural variations in dust storms, brief electromagnetic disturbances, or routine atmospheric phenomena could be misconstrued as signs of cosmic catastrophe or alien interference. Imagine the following nightmarish timeline: a series of seemingly minor occurrences, unexpected brightening, subtle changes in atmospheric composition, or brief electromagnetic glitches, are interpreted by the public and media as confirmation of a planetary disaster. These interpretations could rapidly escalate into widespread panic, conspiracy theories, and misinformation, creating a collective hysteria rooted more in fear than fact. The scenario illustrates how fragile the line is between scientific uncertainty and societal panic, especially when authoritative voices choose caution over sensationalism. Atlas glided past Mars on October 3rd, an event that, on the surface, appeared uneventful, almost mundane. Its approach was marked by only faint, barely perceptible shifts in the planet's electromagnetic field, subtle enough to demand highly sophisticated, nuanced analysis to detect and interpret. Meanwhile, orbiting spacecraft around Mars continued their routines, operating normally, yet under a precautionary pause. They activated safety protocols that temporarily limited their scientific activities, reducing their data collection and transmission efforts as a safeguard against potential unforeseen impacts or electromagnetic disturbances. On the Martian surface, robotic explorers experienced brief communication interruptions. The ionosphere, the planet's electrically charged upper atmosphere, began to fluctuate in unpredictable ways. From a purely scientific standpoint, this scenario represented a fascinating, if somewhat ordinary, encounter with an interstellar object. It offered an opportunity to gather valuable data about how such objects interact with planetary magnetospheres and atmospheric layers. Insights that could deepen our understanding of celestial phenomena and planetary defense mechanisms. Yet from the perspective of public information and media communication, the picture was far more complex. The temporary slowdown in imagery and data transmission from Mars was perceived by many as a deliberate attempt to conceal something significant. The blackout created a visual and informational void, an information vacuum that fueled speculation and conspiracy theories. In the absence of clear, immediate explanations, the official accounts from space agencies, detailing ionospheric propagation effects and standard spacecraft operational procedures, began to sound like bureaucratic doublespeak. These technical, jargon-laden explanations failed to resonate with a public primed for dramatic revelations, and instead appeared as obfuscation or cover-up. Social media platforms quickly filled with increasingly elaborate and sensational theories about what truly transpired during Atlas's passage. Computer-generated images purportedly showing impact craters on Mars or other signs of disturbance circulated at a rapid pace, faster than official corrections or clarifications could be issued. Adding fuel to the fire, amateur radio operators and independent enthusiasts claim to have intercepted emergency transmissions from the orbiters, signals that space agencies publicly refuse to acknowledge or decode. These claims, whether true or fabricated, contributed to an atmosphere of distrust and intrigue. The psychological dynamics behind such information cascades, how rumors and misinformation spread and become entrenched, are well understood by cognitive scientists. Yet despite this knowledge, official communication strategies remained largely unprepared for the rapid, uncontrolled flow of speculation. When audiences are predisposed to expect sensational or catastrophic events, even routine scientific caution or technical explanations are often misconstrued as attempts to hide the truth. Furthermore, when explanations involve complex details, such as ionospheric effects, electromagnetic interactions, or spacecraft safety protocols that demand specialized understanding, they tend to be dismissed as evasive or deliberately opaque. This pattern echoes recent political and social events, such as the 2024 presidential election, where facts and evidence struggled to counteract persistent misinformation. Just as unfounded claims about election fraud persisted despite overwhelming evidence, so too could claims of cosmic cover-ups and data suppression take root amidst uncertainty and mistrust. The situation becomes even more tangled when considering the international dimension. Different space agencies operate under varying protocols, political constraints, and communication styles. For instance, the European Space Agency, which often follows different scheduling and information-sharing conventions than NASA, might release updates on their own timetable, dates that do not align with NASA's, or that emphasize different aspects of the encounter. This lack of synchronized messaging can foster suspicion, leading to the perception of disjointed or conflicting narratives, further fueling conspiracy theories and public confusion. In sum, the public's perception of the Atlas encounter was shaped as much by psychological and informational dynamics as by the event itself. Without clear, compelling, and accessible explanations, the natural tendency to fill informational voids with speculation can quickly spiral into widespread misinformation, distorting the collective understanding of what actually transpired. These discrepancies in timing could easily be misinterpreted as signs of poor coordination or intentional manipulation of information, rather than mere operational adjustments. In particular, amateur astronomers across different nations, each governed by unique transparency standards, might record and share observations that directly contradict or complicate official narratives. Such conflicting reports could expose gaps or biases in the official story, adding layers of complexity to the global understanding of what truly transpired. Furthermore, space agencies from countries like China and Russia, operating under distinct political pressures and strategic priorities, might interpret and describe the same event in ways that appear inconsistent with the accounts provided by Western institutions. These differing perspectives, shaped by varying motives and constraints, could contribute to an increasingly fragmented information environment. As a result, multiple conflicting versions of the truth would compete for public attention, with scientific accuracy becoming just one of many variables influencing which narrative ultimately gains dominance. Perhaps most insidiously, the so-called "don't look up" scenario might become self-fulfilling if mounting public pressure pushes agencies to prematurely disclose preliminary scientific findings that later prove to be incorrect or incomplete. In the face of congressional inquiries and relentless media scrutiny, space agencies could feel compelled to release tentative results simply to satisfy the demand for transparency. However, these early disclosures often lack the thorough validation required for scientific rigor. When subsequent more rigorous analyses correct or refine these initial claims, the discrepancy between early and later findings could be exploited by critics as evidence of incompetence or even deliberate deception, rather than a normal part of scientific progress. This pattern, initial dramatic assertions followed by cautious corrections, mirrors the familiar tropes fueling conspiracy theories that allege government cover-ups or institutional dishonesty. Over time, such cycles of overstatement and correction could erode public trust in space agencies, undermining decades of credibility built through successful missions and groundbreaking discoveries. The long-term repercussions for space science could be profound. As public confidence diminishes, future missions might face increasingly skeptical audiences, conditioned over time to doubt official explanations of astronomical phenomena. The result could be a more cautious, less ambitious approach to exploration, hampered by the lingering suspicion that authorities are withholding or manipulating vital information. Yet, even as we grapple with these potential information crises, we must prepare for the possibility that October 3rd might come and go without providing clear answers to the many questions Atlas has raised. What occurs when a landmark astronomical event, perhaps the most significant of our generation, ends with more unresolved mysteries than resolved truths? What if the universe, in its inscrutable indifference, refuses to deliver the dramatic closure that human psychology instinctively craves? This leads us to a sobering reflection: the potential for the universe to deny us that final, satisfying resolution. Instead, we might find ourselves left with lingering questions, unresolved uncertainties, and the uncomfortable realization that some cosmic mysteries may remain forever out of reach, challenging our understanding of the universe and our place within it. The celestial object, approximately 400 meters in diameter, was unlike any other material humanity had encountered before. Composed of exotic ices and complex organic compounds, its makeup defied the familiar chemistry of our solar system, indicating origins from a distant stellar environment where such substances could form. Conditions that had never been realized within our own cosmic neighborhood. As this interstellar wanderer hurtled towards Mars, it delivered an impact of staggering power, equivalent to the explosive force of several thousand nuclear weapons, upon a planet completely unprepared for such cosmic violence. Within moments of collision, orbiting reconnaissance instruments captured images that would resonate through the scientific community for generations to come. An immense, expanding fireball erupted, briefly surpassing the brightness of the sun in Mars' pale, dusty sky, casting a ghostly glow over the barren landscape. This fiery display was succeeded by a shockwave that tore across the planet's surface at hypersonic speeds, obliterating everything, rock, dust, and ancient ice, in its relentless path. When the dust finally settled and orbital observations resumed, they revealed a colossal crater, measuring 37 kilometers across, a fresh wound in Mars' ancient crust. This scar exposed geological formations that had remained hidden since the planet's earliest days, untouched since the dawn of its geological history. Yet this impact crater was merely the opening act in a transformation that threatened to turn Mars into an alien, unrecognizable world. The collision had excavated millions of tons of subsurface permafrost, frozen water ice that had been locked in the Martian crust for billions of years, and vaporized it instantaneously. The sudden release of this water vapor into the planet's tenuous atmosphere sparked weather phenomena that defied all existing climatological models. Within hours, massive storm systems emerged, driven by temperature differentials and atmospheric dynamics that had never before been observed in Mars' recorded history. Simultaneously, the impact unleashed an electromagnetic pulse of extraordinary intensity, an energetic burst that overwhelmed every piece of human technology orbiting the planet. The fleet of Mars-bound spacecraft, including the Mars Reconnaissance Orbiter MAVEN, Mars Express, and the Trace Gas Orbiter, our robotic eyes and ears, were caught in this electronic onslaught. Their systems, designed for routine operations, immediately triggered emergency safe mode protocols. Their star trackers, critical for maintaining orientation, lost lock, and radio communication systems were flooded with radio frequency interference from the ionized debris cloud generated by the collision. Ordinarily, safe mode is a temporary safeguard, meant to shield spacecraft from brief anomalies. But in this catastrophic scenario, the conditions were anything but temporary. The electromagnetic chaos persisted, disrupting the delicate balance of onboard systems and rendering them increasingly vulnerable. As backup power sources dwindled and critical components failed under stresses they had never been engineered to withstand, the orbiters gradually fell silent, one after another. The communication blackout with Mars endured for 14 months, more than a year during which humanity had no direct link to the planet that had long symbolized our aspiration for cosmic exploration. The robotic explorers, Perseverance, Curiosity, and the international fleet of landers, disappeared into radio silence, their signals ceasing altogether. Back on Earth, the psychological impact was immediate and profound. Mars, the next step in humanity's grand voyage into the cosmos, had become a ghost planet, a silent, unresponsive remnant of hope. It represented our collective dreams of expansion, discovery, and the dawn of a new era beyond our home world. To witness its sudden and inexplicable disappearance from our technological reach was akin to witnessing the destruction of humanity's most cherished aspirations. The loss struck at the core of our cosmic ambition, leaving scientists, policymakers, and the public alike stunned, grappling with a sense of profound helplessness in the face of an event of cosmic scale and unimaginable violence. Stock markets plummeted sharply as the shockwave of catastrophic events rippled through financial corridors worldwide, causing aerospace giants to see their ambitious Mars exploration contracts dissolve into nothingness overnight. The sudden vacuum in scheduled missions sent a ripple of uncertainty through the industry, and congressional hearings erupted with urgent demands for explanations that no one could plausibly supply. As emergency protocols were activated and hastily launched replacement satellites scrambled to restore communication links, the Mars that re-emerged from the depths of radio silence bore scant resemblance to the familiar world we once knew. The impact had profoundly disrupted the planet's entire atmospheric circulation, shattering the stability of what had been a relatively predictable climate system. Before this upheaval, Mars's weather was characterized by seasonal dust storms and well-understood meteorological patterns, predictable enough for mission planning and scientific study. But now, chaos reigned. Once rare and sporadic dust storms, occurring only every few Martian years, had become the new constant, an unrelenting, planet-wide phenomenon. The surface was perpetually veiled beneath a thick shroud of suspended particles, a suffocating curtain that blocked sunlight and rendered solar power generation unreliable, crippling surface operations and long-term planning alike. Temperatures, once modulated by atmospheric conditions, plummeted as the dense, dust-laden atmosphere reflected the incoming solar radiation back into the cold void of space. This feedback loop triggered what could only be described as a planetary-scale nuclear winter, lasting for more than 3 Martian years, engulfing the planet in a prolonged period of climatic darkness. The radioactive environment around Mars had been forever altered by the impact. The collision had not merely displaced ancient surface materials, it had also lofted radioactive substances from deep within the Martian crust, scattering them across the atmosphere and beyond. In addition, the impact had spawned a chaotic debris ring, a tumultuous halo of impact ejecta that lingered in orbit, bombarding the upper atmosphere with fragments for months. This debris cloud created persistent auroral displays and ionospheric disturbances, which intermittently interfered with radio communications, making signal transmission sporadic and unreliable. The collateral damage extended further. Phobos, Mars's larger, irregularly shaped moon, had suffered its own share of destruction. Impact debris from the surface collision had struck Phobos with sufficient force to destabilize its already precarious orbit. Instead of the slow, predictable petosat million-year spiral that astronomers had anticipated, an inevitable end in a distant future, the moon began fragmenting almost immediately. This fragmentation gave rise to a debris field that would cast a shadow over Mars's orbital environment for centuries. The fragments, ranging from boulder-sized chunks to massive building-sized debris, followed chaotic and unpredictable orbits, turning navigation through Mars's vicinity into a deadly game of cosmic roulette. Any spacecraft attempting to reach the planet would have to meticulously thread its way through a sprawling three-dimensional minefield of rocky remnants, moving at velocities that would turn even minor collisions into catastrophic events. The visions of establishing colonies on Mars, which had seemed tantalizingly close just a few years earlier, dissolved amid the radioactive dust clouds that now cloaked the entire planet in a permanent shroud. The meticulously planned Artemis Mars missions were canceled indefinitely, their objectives now rendered impossible. The international treaties governing Mars exploration, once seen as a framework for peaceful scientific cooperation, became obsolete overnight, as the planet they aimed to protect had become too dangerous to visit. Private enterprises that had poured billions into Mars transportation systems faced a devastating blow. Their models, predicated on a relatively stable environment, were shattered by cosmic catastrophe. SpaceX's Starship, originally designed for cargo delivery to Mars, was hurriedly repurposed for lunar missions and asteroid mining operations, its future now uncertain and its original mission paradigms disrupted beyond recognition. Before they ever took to the skies, Blue Origin's Mars landing systems had already become relics. Museum pieces gathering dust in forgotten warehouses, their sleek designs and cutting-edge technology rendered obsolete before a single mission could be launched. The scientific community faced the staggering task of comprehending the enormity of what had been lost, an entire chapter of planetary exploration wiped away in an instant. Mars had long stood as humanity's natural laboratory for unraveling the mysteries of planetary evolution, deciphering the complex dance of climate change, and probing the age-old question of whether life might exist beyond Earth's bounds. The rovers and landers, which had tirelessly spent decades meticulously analyzing Martian soil, minerals, and atmospheric conditions, were now buried beneath layers of radioactive debris, silent witnesses to a cosmic catastrophe that had erased their discoveries forever. The most devastating realization, however, was not merely the physical loss of these invaluable assets, but the profound concept of time itself. The Mars that Atlas had obliterated was irreplaceable within the span of human history. An environment that had taken billions of years to evolve into a world both familiar and tantalizingly close to habitability. While planetary atmospheres can, under certain conditions, recover from catastrophic disruptions, such processes are painstakingly slow, often spanning millions of years. The Mars that might eventually rise anew from the chaos Atlas had unleashed would be fundamentally different from the world that had beckoned to explorers and scientists for generations. Its very nature had been altered. Its axial tilt shifted slightly, subtly but meaningfully changing the planet's seasonal rhythms, a change that would take decades, perhaps even centuries, to fully comprehend and adapt to. The injection of vast quantities of water vapor and exotic organic compounds released from Atlas's nucleus had triggered atmospheric chemistry that defied terrestrial models and expectations. This was no gradual terraforming, no carefully calibrated release of greenhouse gases designed to coax Mars into a more Earth-like state. Instead, what unfolded was a rapid, chaotic planetary transformation, a planetary upheaval that rendered all prior Mars exploration plans and the dreams attached to them obsolete overnight. The cascade of consequences extended far beyond the red planet itself. The destruction of what had been humanity's most accessible stepping stone to the outer solar system compelled a comprehensive reevaluation of our trajectory into space. No longer could Mars serve as a convenient staging ground for missions heading toward the asteroid belt or the moons of Jupiter. Space agencies were suddenly faced with the daunting challenge of developing more complex, more costly, and more direct routes to these destinations. Routes that bypassed Mars entirely, venturing straight into the deeper reaches of the solar system. The psychological toll was equally profound. Witnessing our cosmic neighbor, a symbol of human ambition and curiosity, become uninhabitable in an instant instilled a generation of space scientists with suspicion rather than wonder. The romantic ideal of comets and interstellar objects as harbingers of cosmic beauty and discovery was replaced by a stark, pragmatic understanding. The universe harbors forces capable of annihilating worlds without warning or malice. As evidence of this new reality became undeniable, governmental support for planetary defense initiatives surged. Congressional funding for planetary protection programs increased dramatically, transforming what was once a niche area of research into a cornerstone of our long-term survival strategy. The success of the DARK mission, initially celebrated as a technological achievement in deflecting asteroid Dimorphos, suddenly took on new significance. It was no longer merely a demonstration of human ingenuity, but the foundation of a multi-billion-dollar effort to safeguard Earth and its neighbors from catastrophic cosmic impacts. This shift was driven by a sobering truth. If Atlas, an interstellar visitor passing through our solar neighborhood by chance, could obliterate Mars in a single encounter, what other silent, unseen interstellar travelers might be approaching us? Objects capable of bringing even greater devastation? In the shadow of that disaster, humanity's perspective on the cosmos had irrevocably changed. We no longer saw the universe as a benign expanse filled with celestial beauty and promise. Instead, we recognized it as a realm of unpredictable and often hostile forces, powerful, indifferent, and capable of erasing worlds in the blink of an eye. The cosmic neighborhood, once thought to be a relatively safe arena for exploration and discovery, had revealed its darker side. The haunting question now loomed: how many other interstellar visitors quietly journeying through the void might be silently approaching, carrying with them the potential for catastrophe far beyond our current understanding? The universe had sent a stark message, one we could no longer afford to ignore. The global network of observatories and tracking systems initially devised to monitor near-Earth asteroids was swiftly and extensively expanded in the years leading up to Atlas's passage. This upgrade was motivated by a newfound understanding that the universe is far from a tranquil, empty void. Instead, it teems with wandering objects, cosmic nomads capable of altering or even obliterating planets on timescales that dwarf geological epochs. The once-held belief that space was a safe, predictable frontier was replaced by a sobering reality. Our cosmic neighborhood is filled with unpredictable visitors, some potentially dangerous, moving swiftly enough to pose a threat to our planetary stability. But as we reflect on this alternate history where Mars faced destruction on October 3rd, it is crucial to recognize that the universe rarely delivers such definitive closure to its mysteries. The dramatic narratives of cosmic catastrophe often give way to subtler, far more enigmatic phenomena. What if Atlas's encounter with Mars turned out to be far less a grand, catastrophic event and more a whisper? A quiet ripple in the fabric of space that leaves us with more questions than answers about our vulnerability in the cosmos. If by some chance Mars survived this cosmic brush, then October 3rd passed like a mere whisper rather than a deafening scream across the void. The final trajectory calculations by the European Space Agency placed Atlas at its nearest approach to Mars, precisely 30.2 million kilometers. At exactly 11 hours, 17 minutes Universal Time. In the grand scale of cosmic distances, this sounds reasonably close, about 75 times the distance from Earth to our moon. Yet this proximity was enough to warrant intense scrutiny, and it was far too close to be considered completely safe. Remarkably, no impact occurred, no electromagnetic storms erupted, no planet-wide dust storms or radioactive chaos consumed the red planet. Mars, with its ancient orbit around the Sun, continued unperturbed, seemingly oblivious to the close encounter with this interstellar visitor. 6 hours after the closest approach, the first official statement emerged from ESA Mission Control. Their brief report succinctly conveyed that Atlas had completed its Mars encounter within all predicted parameters. Their instruments, orbiters, and sensors detected nothing out of the ordinary. Mars's orbit and surface operations appeared normal. No anomalies, no signs of disturbance, and no immediate threat. The message, composed of just 42 words, managed to sound both reassuring and deeply unsatisfying at the same time. It was a statement of normalcy, yet it left unanswered the profound questions that had gripped the world for months. Within moments of this announcement, the social media landscape exploded with a collective sense of anticlimax bordering on indignation. "That's it," became the most trending phrase on Twitter within the hour, a reflection of the public's longing for drama, for a story with a decisive climax. Reddit forums dedicated to Atlas speculation quickly descended into bitter debates. Was this outcome a triumph of prediction, a testament to our understanding, or was it evidence of a covert cover-up? The shared disappointment revealed something fundamental about human psychology and our complex relationship with cosmic events. For months, Atlas had captured the world's imagination precisely because it embodied the unknown, the potential for catastrophe, the thrill of discovery, the cosmic significance of an alien visitor from beyond our solar system. Its mysterious behavior, erratic brightness, and interstellar origins had fueled theories ranging from scientifically plausible to utterly fantastical. All these speculations, however, operated under a common assumption. When this alien messenger reached its closest point to Mars, something dramatic would happen. The universe, in our minds, was supposed to deliver a grand spectacle. Yet the harsh reality of cosmic encounters often defies narrative expectations. The universe obeys physical laws that are indifferent to human desires for meaningful resolution or dramatic closure. Most astronomical events, even those of genuine significance, such as a comet's approach or a planetary collision, tend to unfold in ways that appear mundane to observers untrained in recognizing their subtle but critical implications. What appears as a simple, uneventful flyby from our perspective might hold complex hidden truths that only reveal themselves through diligent analysis over time. In the end, the universe's quiet, unremarkable unfolding serves as a humbling reminder. Our human narratives are often too limited to grasp the full scope of cosmic reality. The universe, it seems, has little interest in providing the climactic endings we crave. Instead, it moves forward with a detached, inexorable logic, quietly revealing its secrets only to those willing to look beyond the surface, those trained to notice the subtle signs, the faint whispers of cosmic change that often go unnoticed by the casual observer. 12 hours after Atlas' closest approach to Mars, NASA issued a follow-up statement that carefully outlined the technical details of the encounter. While these details undeniably satisfied the curiosity of the scientific community, they simultaneously dashed the public's hopes for a dramatic revelation. The preliminary data analysis indicated only minor variations in Mars's ionosphere, subtle shifts in ionospheric density that aligned well with what scientists had anticipated from interactions between Atlas's ion tail and Mars's weakened magnetic environment. Crucially, no structural damage to orbiting spacecraft was observed, and surface operations on Mars continued smoothly and without interruption. The language used in the official communication was precise, measured, and entirely professional, utterly lacking the sensationalism and awe-inspiring spectacle that months of speculation had led many to expect. This raised an obvious question. Where were the breathtaking images of Atlas streaking past Mars? Where were the luminous electromagnetic displays, the auroras and light shows that terrestrial telescopes should have captured during such a momentous event? Where were the undeniable signs that something historically significant had taken place in the course of this encounter? The disappointing answer lay in the nature of the phenomena itself. Most of the dramatic effects that had fueled public anticipation, mind-blowing visuals and spectacular light shows, would have been largely invisible to casual observers. Variations in ionospheric density, although profoundly important to scientists understanding the subtleties of interstellar object interactions, do not translate into visual spectacles. Similarly, the interactions between Atlas's ion tail and Mars's magnetosphere, although vital for advancing our knowledge of cosmic bodies, produce data rather than images. Expert astronomers understood that the most significant consequences of Atlas's passage, such as long-term gravitational influences, trace atmospheric chemical reactions, and the subtle effects on Mars's electromagnetic environment, might not become clear for months or even years. These effects require meticulous extended analysis of the collected data, which involves months of careful interpretation and observation. However, the vast majority of the public's attention is governed by the relentless news cycle, which demands instant gratification. When the October 3rd encounter did not deliver the expected visual fireworks, the story quickly lost its narrative momentum. The vacuum created by the absence of immediate dramatic visuals was swiftly filled with speculation and conspiracy theories, as eager minds sought explanations for the perceived lack of spectacle. If nothing extraordinary had happened, skeptics questioned, then why had space agencies been so secretive about their observational plans? Why were there so few publicly released images? Why did official statements rely heavily on technical jargon and omit any mention of visible phenomena? Amateur astronomers who had dedicated weeks to observing and capturing the event with their own telescopes found themselves in an awkward position. Their images, which documented Atlas's passage near Mars, showed nothing particularly remarkable. No fiery trails, no flashing lights, no celestial fireworks, merely predictions that had been available for months. Even the most advanced ground-based observatories faced similar challenges. Their detailed spectroscopic measurements, which revealed minuscule shifts in Atlas's emission patterns, were of enormous scientific value but lacked the visual impact that typically captures the public's imagination. These subtle changes in spectral lines and emission signatures are important indicators of the physical and chemical processes at play. But they do not produce the kind of eye-catching imagery that makes headlines or captivates social media audiences. Most importantly, professional astronomers recognize that the true significance of Atlas's encounter with Mars would likely not manifest immediately. The long-term effects, such as delicate gravitational perturbations, slight alterations in atmospheric chemistry, and the evolving electromagnetic environment, would require months or even years of dedicated monitoring and analysis before their implications could be fully understood. Yet, in our modern age of instant information, the public's thirst for immediate spectacle often leaves little room for patience or nuanced scientific interpretation. As a result, the story of Atlas, which had maintained media interest for months through layers of mystery and speculation, suddenly lost its momentum. The conspicuous absence of dramatic visuals during the encounter created a conspicuous information vacuum. Conspiracy theories and sensationalist narratives quickly filled the void, claiming that space agencies were deliberately withholding spectacular evidence or hiding some hidden catastrophe. Skeptics argued that the lack of images and the technical nature of official reports pointed to a cover-up. Meanwhile, amateur astronomers who had spent weeks preparing for the event found themselves facing the reality that their own observations, which documented Atlas's passage, revealed nothing more extraordinary than what the predictions had already suggested. Their telescopic images showed no blazing cometary tail or dazzling celestial fireworks. Instead, the footage simply confirmed what had been carefully modeled and anticipated. These images, while scientifically invaluable, failed to produce the visual impact that would have captured the imagination of the broader public. Similarly, the most sophisticated observatories and spectrometers around the world faced challenges translating their detailed data into compelling images. The subtle spectral signatures indicating changes in Atlas's emission patterns are hidden in technical reports. They are crucial for understanding the physical processes but do little to inspire awe. These measurements, while vital for scientific progress, do not lend radiotelescopic arrays detected subtle fluctuations in plasma density surrounding Mars, a discovery that in itself was a significant scientific achievement. Yet, these findings lacked the visual spectacle that captures the public's imagination and fuels widespread excitement. In the age of social media, algorithms are tuned to prioritize engagement over education, amplifying sensational narratives and often distorting the true nature of scientific results. As a result, the relatively mundane but crucial data from these observations were quickly transformed into the supposed evidence of a cover-up, with many interpreting the careful, systematic approach characteristic of professional astronomy as deliberate obfuscation. Many members of Congress who had previously leveraged ATLAS as a high-profile platform to advocate for space funding and planetary defense initiatives now found themselves in an awkward and uncomfortable position. They had promised their constituents dramatic revelations, images of cosmic fireworks, catastrophic impacts, or extraterrestrial signals. Yet the encounter resulted in only subtle data and unremarkable findings. This disconnect between expectations and reality fueled frustration and suspicion among the public. In response, the House Science Committee hastily rebranded scheduled hearings on ATLAS from urgent crisis discussions into routine oversight sessions focused on NASA's Mars exploration programs. The shift was swift, and the media landscape responded in kind, transforming what was initially a story of potential cosmic peril into an anticlimax. Major cable news outlets, which had prepared extensive programming and countdowns to the ATLAS encounter, suddenly found themselves with hours of airtime to fill but very little sensational content to justify the buildup. Expert panels assembled to discuss the possibility of cosmic catastrophe instead found themselves explaining that the absence of dramatic events was, in fact, the most probable and reassuring outcome. The scientific community faced its own set of public relations challenges. Researchers who had dedicated months to preparing for the ATLAS observation campaign discovered that their preliminary results, rich with spectral signatures indicating the presence of exotic chemical compounds, failed to ignite the public's sense of wonder. These subtle, scientifically important details did not translate into the kind of visual spectacle that sustains funding and public interest. Furthermore, the seamless international cooperation among agencies such as NASA, the European Space Agency, and JAXA, an unprecedented level of coordination in planetary observation, received surprisingly little media attention. This smooth collaboration, which prevented conflicting or sensationalized information from proliferating, was seen by some as a sign of transparency, but others dismissed it as a cover-up. The high-resolution infrared images captured by the James Webb Space Telescope during the ATLAS encounter, showcasing some of the clearest views of an interstellar comet ever obtained, were overshadowed by public disappointment. The images did not depict the fiery impacts or alien invasions that had been widely speculated upon before the encounter. Instead, they revealed subtle spectral signatures, indicative of complex chemistry, that were inherently less visually arresting. Amateur radio operators who had fervently prepared to monitor potential electromagnetic disruptions in Mars's communication networks found themselves recording routine operations instead. The anticipated cosmic chaos, flashes of plasma, bursts of electromagnetic interference, and signals of extraterrestrial origin, failed to materialize, leaving many observers documenting nothing more than the ordinary functioning of spacecraft systems. This stark contrast between expectation and reality fueled skepticism, conspiracy theories, and a sense of disillusionment among enthusiasts and the general public alike. Their highly advanced and meticulously calibrated monitoring systems designed specifically to detect and record phenomena of profound cosmic significance had been diligently set up in anticipation of the Atlas encounter. These instruments aimed to capture evidence that could potentially reshape our understanding of interstellar objects and their interactions with our solar system. Yet, rather than unveiling spectacular or unprecedented activity, they instead documented the subtle but reassuring steadiness of ongoing Mars exploration operations. Routine images, steady data streams, and the familiar hum of robotic activity. The anticipated dramatic event, the one that many had braced themselves for, never materialized in any visually striking way. This absence of spectacle on October 3rd began to take on a symbolic weight that extended far beyond its initial astronomical context. It transformed into a kind of subtle cultural touchstone, a reflection of broader issues in science communication and public engagement. Critics and observers pointed to the Atlas anticlimax as a sign of a deeper institutional failure, an inability of scientists and space agencies to properly manage expectations in an age where the public's fascination is often driven by sensationalism and spectacle. They argued that despite the scientific community's efforts to communicate the complexities of the event, there was a disconnect. Researchers and agencies had perhaps overestimated the public's appetite for nuanced, subtle discoveries and underestimated the importance of clear, transparent messaging about what was truly significant. What was always most likely to be an event of great scientific interest, yet visually unremarkable, had been presented in a way that set the stage for disappointment. Educational institutions found themselves caught in a similar dilemma. Teachers and professors, who had been following Atlas as a real-time case study in the behavior of interstellar visitors, observed a rapid decline in student engagement once the encounter failed to produce the anticipated drama. The classroom discussions that had been lively and focused on the potential implications of interstellar debris, exotic chemistry, and gravitational perturbations suddenly faced a waning audience. Students conditioned by a media landscape obsessed with visuals and sensational stories struggled to maintain interest in the subtle, often complex scientific discoveries that the event actually revealed. Discoveries that could have profound implications for our understanding of the cosmos. The challenge for educators became clear: how to keep students engaged with the understated yet fundamentally important nuances of planetary science in an era dominated by instant gratification and spectacular imagery. Meanwhile, the long-term implications for public support of space science began to emerge as a growing concern within the astronomical community. If the most remarkable interstellar visitor in human history could traverse the inner solar system without capturing sustained public imagination or media attention, then future missions, perhaps even those with far more tangible benefits, might struggle to command the necessary attention and funding. The challenge of maintaining a broad societal commitment to space exploration grew even more urgent, especially considering terrestrial concerns that often overshadow scientific priorities. The rapidity with which public interest shifted away from Atlas was striking. Within mere weeks, the comet that had dominated headlines and media cycles for months was almost entirely forgotten by mainstream outlets. The detailed scientific analysis of the encounter, crucial for understanding the true nature of Atlas and its potential impact, remained largely outside the public eye, its value obscured by the fleeting focus on more immediate terrestrial issues. This swift transition in public attention risked blinding us to the subtle signals that Atlas's influence on our solar system was far from over. What if the apparent quietness of the Mars pass-by was merely the opening chapter of a far more complex cosmic narrative? What if the real story, the deeper, more profound implications of Atlas's passage, was just beginning, concealed behind layers of institutional secrecy, strategic ambiguity, and a general public indifference to the quiet unfolding of cosmic events? Could this be a prelude to a much larger, more intricate symphony of interstellar interactions? This idea leads us into a broader perspective, one where Atlas is not simply a fleeting visitor but a messenger, carrying information, signals, or perhaps even warnings from realms beyond our direct experience. For centuries, humanity's understanding of comets has been intertwined with symbolism and myth. Throughout history, comets have punctuated the narrative of civilization. They have served as harbingers of change, symbols of transformation, messengers from distant, unknowable worlds. Ancient astronomers interpreting these fiery visitors with reverence and curiosity often saw them as divine signs, warnings or messages encoded in celestial fire that demanded careful decoding by wise interpreters. These interpretations were rooted in the belief that the heavens communicated directly with humanity, conveying secrets of cosmic significance. Now, Atlas arrives in our solar system, bearing credentials that defy any of our previous understandings. It is not a typical comet following a predictable, calculable orbit, one that can be mapped decades in advance with confidence. Instead, this object, unlike anything in our celestial catalog, possesses an origin story, an interstellar lineage that makes it a true outsider, a cosmic messenger from realms far beyond the familiar confines of our sun's gravitational domain. It carries within its nucleus a kind of celestial dossier, containing signatures of stellar environments that no longer Atlas is not merely an ordinary comet drifting through the void. It is, quite possibly, a vessel of profound significance, an authentic alien messenger traveling from stellar realms so distant that its very core bears the chemical fingerprints of environments long extinct. Within its nucleus lie the telltale signatures of stellar systems that may have ceased to exist eons before Earth's continents took shape in their current form. These signatures tell tales of stellar winds from exotic suns, radiation fields unlike anything observed in our solar neighborhood, and gravitational forces so intense and unusual that they have sculpted matter under conditions entirely alien to us, all governed by the same unchanging laws of physics that our universe obeys but operating at extremes beyond our natural experience. Every spectroscopic analysis of Atlas's emissions unveils a storybook of cosmic chemistry, stories written in the language of atomic structures, the ratios of isotopes, and the configurations of crystalline matrices that are products of environments never replicated on Earth or within our solar system. Such detailed chemical signatures serve as cosmic fingerprints, revealing the history of worlds that no longer exist, their stellar winds, radiation fields, and gravitational influences all encoded in the very fabric of the comet's composition. It's as if Atlas carries a library of ancient stellar environments, preserved in a cryogenic state, waiting to be deciphered. But what if these chemical signatures are more than just relics of bygone stars? What if the peculiar patterns we observe, the unpredictable fluctuations in brightness, the unusual geometries of the chromatic emissions, the unexpectedly large quantities of carbon dioxide being released, are not random anomalies of a typical comet, but deliberate signals woven into its very behavior? Could it be that what we are witnessing is the first deliberate attempt at interstellar communication, employing a medium we never even considered monitoring, namely, the controlled sublimation of exotic ices? Imagine the possibility that an advanced civilization, masterful in large-scale engineering, has embedded a message within the comet's orbital and emission characteristics, deliberately crafting patterns that can be detected across light years of space. Such a civilization could manipulate the sublimation process to produce specific variations in brightness or spectral signatures, encoding information in ways that only a sufficiently sophisticated observer would recognize. Over months or even years, as Atlas approaches our star system, it could serve as a slow-motion beacon. A carefully orchestrated signal that once decoded might reveal insights about its origin, purpose, or the very existence of its creators. The mathematics behind such a form of communication would be elegantly simple yet profoundly effective. Binary data could be encoded through variations in the comet's brightness, patterns that stand out sharply from the natural fluctuations caused by solar heating or other cosmic phenomena. Spectroscopic signatures, too, could be crafted with precision, with emission line ratios that only reveal their intended message after meticulous analysis. An interstellar Morse code concealed within the comet's gaseous outbursts. Even the comet's trajectory itself could carry encoded information. Subtle course corrections during approach, creating geometric patterns or orbital shifts that serve as unmistakable signatures of intelligent control. From this perspective, Atlas's behavior takes on a new, startling significance. The enormous coma of carbon dioxide that has puzzled astronomers might not be a mere consequence of random sublimation, but could be a controlled gas release, an engineered display designed to maximize the comet's visibility across interstellar distances. The erratic brightness variations, which deviate from expectations based on standard comet models, might be structured signals, an intentional pattern waiting to be deciphered by those with the right analytical tools. The timing of its arrival, coinciding with humanity's recent technological advancements that allow for detailed spectroscopic examination of interstellar objects, might therefore be more than a cosmic coincidence. It could be a carefully orchestrated event, an interstellar message sent in the language of physics and chemistry, crafted to be recognized only by civilizations capable of understanding its underlying code. If this enigmatic object originated from a distant star system thousands of years ago, its journey through the cosmos would have been meticulously calculated, designed to ensure it arrived at our solar system precisely within a narrow window, an epoch when humanity's technological capacity had just reached the point of deciphering complex chemical signals. The advent of the James Webb Space Telescope, NASA's most sophisticated instrument for analyzing the chemical makeup of far-flung celestial bodies, coincides strikingly with this moment. Its deployment marks a new era in our ability to scrutinize interstellar visitors, enabling us to extract far more detailed information from a single object than was conceivable even a decade prior. The timing of Atlas's approach, just as this revolutionary observatory becomes operational, opens unprecedented opportunities. It places us at the cusp of potentially decoding messages embedded within the object's chemical signatures. Messages that could have been encoded eons ago, waiting for humanity's technological evolution to reach a critical threshold. We may be the very first generation capable of unraveling such interstellar communications, should they exist. Meanwhile, coordinated observation campaigns orchestrated by the European Space Agency have amassed an extensive trove of data, more comprehensive than any collected before from a single interstellar object. Within the vast data sets of spectroscopic readings, orbital measurements, and emission patterns lie clues that could reveal patterns or anomalies detectable only through advanced computational analysis. Techniques that did not exist when previous interstellar travelers such as Oumuamua traversed our solar neighborhood. Deciphering a potential interstellar message, however, demands a radical departure from human-centered assumptions about communication. Instead of conventional language or signals, the embedded information might be encoded in universal mathematical relationships. Prime number sequences hidden within brightness variations, geometric constants embedded in spectral line ratios, or physical constants expressed through isotopic compositions that only an artificial, technologically advanced intelligence could manipulate. The real challenge lies in distinguishing these subtle, potentially deliberate signals from natural phenomena. patterns that, while exotic, may simply be products of entirely natural processes shaped by conditions vastly different from our solar system. Interstellar objects inherently behave in ways that defy the norms established by objects born within our stellar neighborhood. Their formation and evolution occur under entirely different stellar environments, leading to behaviors and signatures that may seem anomalous or inexplicable by current models. Isolating true anomalies, signs of artificial origin, requires analytical techniques still in development, pushing the boundaries of our scientific understanding. The contribution of amateur astronomers and citizen science groups becomes invaluable here, as they can offer long-term monitoring data that professional observatories constrained by scheduling and resource limitations might overlook. These dedicated observers, continuously tracking ATLAS over extended periods, could detect patterns or signals most apparent in persistent data streams, clues that might be missed in fleeting professional observation windows. The SETI Institute has quietly begun applying radio astronomy-inspired signal analysis techniques to the datasets collected from ATLAS, seeking signs of artificial manipulation or embedded messages. While no results have yet been publicly announced, the fact that such investigations are underway underscores how seriously researchers are considering the possibility that ATLAS might serve as a platform for interstellar communication. The idea that an object, seemingly just a cosmic visitor, could be a message-bearing device from an extraterrestrial civilization is being taken into account. An extraordinary prospect that challenges our understanding of cosmic interactions and our place within the universe. The message, if one indeed exists, may not be crafted for our immediate understanding or interpretation. If it is of interstellar origin spanning thousands of years of cosmic travel, then the concepts, symbols, or information it contains might be encoded in ways that surpass our current comprehension, requiring future generations' scientific and mathematical advancements to unlock its true meaning. ATLAS could be transmitting a message designed to reveal itself only when humanity's collective knowledge reaches a level of sophistication comparable to that of the civilization that originally sent it. This notion suggests that the true significance of such a communication might be layered in complexities that lie dormant until our understanding of the universe's fundamental principles evolves sufficiently. The psychological impact of discovering that we are not alone in the universe, delivered through the deliberate, patient arrival of an interstellar message, would be nothing short of transformative. It would fundamentally alter our worldview, challenging deeply held notions about humanity's solitary place in the cosmos. Such a revelation would force us to reconceptualize our responsibilities, our ethics, and our relationships within a galactic network of intelligent civilizations, spanning countless star systems and perhaps varying levels of technological and cultural development. It would mark a turning point in human history, reshaping our identity and our sense of purpose on an unprecedented scale. However, the absence of an immediately recognizable or obvious message should not be taken as evidence that no message exists at all. The most advanced forms of communication, perhaps embedded within the very behavior or subtle emissions of ATLAS, might be encoded in ways that we have yet to develop the tools to detect or interpret. Future analytical techniques, innovative algorithms, or breakthroughs in quantum or information science could one day reveal patterns, signals, or messages hidden in the data we currently consider mundane or indecipherable. Generations from now, scientists might look back at our current observations of ATLAS and marvel at the wealth of information we failed to recognize. An enormous yet largely unexploited interstellar dataset that could hold the key to understanding not only this object, but perhaps other cosmic messages yet to come. The international scientific community's collaborative efforts in studying ATLAS have created a unique and unprecedented opportunity for global cooperation. By pooling resources, knowledge, and data, humanity has laid the groundwork for a unified approach to potential message decoding efforts. If Atlas's true purpose is to communicate with all of humanity, rather than to serve the interests of any single nation, then this distributed open-access coordination ensures that no single government or institution can monopolize or suppress the information. Instead, the collective effort becomes a testament to our shared curiosity. Curiosity that transcends borders and political divides, aiming to decipher what could be the most profound message in human history. This encounter with Atlas may inadvertently serve as a test of our civilization's capacity for rational analysis and calm decision-making amid uncertainty and widespread speculation. The theories we formulate, the fears we harbor, and the institutions we place our trust in, these all reveal much about our collective psychological resilience. If we respond with panic or suspicion, or if we allow misinformation to distort our understanding, then our decision-making mechanisms may be vulnerable to catastrophic failure when faced with the more tangible threats of genuine cosmic dangers. The rapid transformation of Atlas into a vessel for fears about government secrecy, extraterrestrial threats, and institutional incompetence underscores how easily our information systems, especially those amplified and manipulated by social media, can be exploited. Today's algorithms tend to prioritize sensationalism and dramatic content, often at the expense of accuracy or nuance. This creates an environment where speculation can outpace scientific evidence, leading to widespread misinformation and confusion. The October 3rd encounter, therefore, transcends its astronomical significance. It becomes a mirror reflecting our civilization's relationship with the unknown, our trust, or lack thereof, in scientific and governmental institutions, and our collective ability to distinguish between genuine mysteries and manufactured crises. It highlights the urgent need for critical thinking, responsible communication, and humility in confronting the profound uncertainties that lie beyond our current understanding of the universe. The insights we gain from Atlas's journey through our solar system may ultimately prove to be far more consequential than any tangible damage this interstellar visitor might cause to Mars or other celestial bodies. Perhaps the most profound understanding emerging from this encounter is of a temporal nature, one that redefines our perspective on the very fabric of our cosmic neighborhood. It reveals that our solar system exists within a vast galactic environment where interstellar visitors are not rare anomalies but routine phenomena. This realization challenges the long-held notion that such objects are extraordinary, instead positioning them as an expected part of the cosmic landscape, occurring regularly within the immense timescales of the galaxy. The infrequency with which such objects appear in human historical records does not necessarily reflect their true scarcity. Rather, it mirrors the brevity of our current technological civilization, an era so short compared to the immense epochs of astronomical time that we have only recently begun to detect and understand these cosmic travelers. The advent of advanced detection capabilities suggests that Atlas may be merely the first of many interstellar visitors that future technologies will reveal. As our observational tools grow more sophisticated over the coming decades, we will likely encounter an increasing number of these objects, each offering new opportunities and challenges for humanity. If this is the case, then our present-day debates, hypotheses, and institutional responses are laying the groundwork for how we will confront the broader phenomenon of cosmic encounters in the future. The frameworks we are now developing, both scientifically and societally, will serve as the foundation for managing similar events as they become more frequent. The protocols, policies, and analytical models we craft today in response to Atlas will shape our collective approach to future interstellar visitors for generations to come. The data collected during Atlas's passage, spectroscopic measurements, orbital calculations, and emission analyses constitute the most comprehensive study of an interstellar object ever conducted by human civilization. These datasets are invaluable repositories of knowledge, offering ongoing research opportunities long after Atlas departs our solar system. Within this vast trove of information, there may lie insights that are not immediately apparent, requiring future technological advances to decode fully. Decades from now, researchers and scholars could uncover hidden patterns and connections within the Atlas data, subtle signatures that our current mathematics or theories are not yet capable of interpreting. The most significant discoveries arising from Atlas's visit might not emerge until the 2040s or beyond, long after current scientists have laid the initial groundwork. When technological progress allows us to revisit and analyze the data with fresh perspectives and more powerful tools, this iterative process of discovery underscores a vital truth. Our understanding of the universe is continually evolving, and what seems obscure today may reveal profound truths in the future. Moreover, Atlas has ignited a remarkable level of international cooperation among space agencies, research institutions, and even amateur astronomers. This unprecedented collaboration exemplifies a new model of global coordination around cosmic phenomena, one that transcends national borders and political boundaries. The protocols established for sharing Atlas data, coordinating observations, and conducting joint analyses could serve as vital templates for managing future encounters with interstellar objects or other cosmic events. Such cooperation not only enhances scientific understanding but also fosters a collective sense of planetary stewardship in the face of the universe's vastness. However, this collaborative approach is not without its vulnerabilities. If our current research efforts regarding Atlas are incomplete, or if we misinterpret critical patterns within the data, the very coordination that allows for comprehensive analysis could inadvertently amplify these errors across multiple institutions and nations. The interconnected nature of these efforts means that systemic mistakes, however unintentional, might be more difficult to recognize and correct, potentially leading to a distorted understanding of what Atlas truly signifies. The contributions of amateur astronomers further demonstrate the importance of a distributed, community-based approach to cosmic observation. Their role in monitoring Atlas has highlighted the enduring value of decentralized networks capable of continuous observation. Unlike professional telescopes, which are limited by scheduling constraints and narrow observation windows, amateur observers can provide persistent, long-term data streams. Their collective efforts form a vital layer of redundancy and resilience, ensuring that no significant detail goes unnoticed and that our understanding remains as complete as possible. In sum, the lessons drawn from Atlas's passage extend well beyond its immediate physical effects. They challenge us to reconsider our place within the galaxy, our preparedness for cosmic surprises, and our collective capacity to respond to the universe's inherent unpredictability. This encounter may serve as a catalyst, prompting us to develop more robust, inclusive, and adaptive frameworks for future cosmic interactions, ensuring that humanity remains vigilant, resilient, and wise in the face of the vast, dynamic cosmos that surrounds us. Looking ahead, the study of future interstellar visitors may be most effectively advanced through carefully orchestrated collaborative endeavors that blend the expertise of professional scientists with the dedication of amateur astronomers, all supported by a broad network of geographic distribution. Such coordinated efforts would harness the strengths of high-end research capabilities alongside the persistent enthusiasm and local knowledge of citizen observers, creating a comprehensive observational tapestry that spans the globe. Educational institutions in particular have already begun to leverage the Atlas encounter as a real-time case study, an invaluable teaching tool that illuminates the complex behavior of interstellar objects. These academic programs are producing pedagogical resources, such as detailed observation protocols, analytical methodologies, and interpretive frameworks that will shape the scientific minds of tomorrow. guiding their approach to unraveling cosmic mysteries for decades into the future. The materials and techniques developed during the ATLAS research, ranging from spectroscopic analysis to orbital modeling, are destined to influence how scientific education evolves, embedding a nuanced understanding of interstellar phenomena within curricula and training programs worldwide. Beyond the scientific, the psychological and cultural repercussions of Atlas's visit may prove as lasting as its tangible contributions to knowledge. This celestial visitor, originating from beyond our solar system, has compelled humanity to confront its own cosmic solitude in ways that mere theoretical discourse could never achieve. The very existence of an object from a distant stellar environment has transformed the perception of interstellar space from an infinite void into a realm more approachable and less alien, an arena where civilizations might indeed coexist or communicate. Throughout Atlas's approach, public opinion polls have captured shifting attitudes, ranging from increased enthusiasm for space exploration and funding to heightened awareness of planetary defense initiatives and a renewed emphasis on international scientific cooperation. These attitudinal shifts, sparked by a single cosmic event, have the potential to influence policy decisions, resource allocations, and strategic priorities that shape humanity's future for generations. Moreover, the Atlas encounter has exposed the profound dependency of our modern technological civilization on the assumption that cosmic conditions remain relatively predictable and stable. Our spacecraft, communication networks, and even terrestrial infrastructure have all been built under the premise that space is a largely unchanging backdrop, punctuated only by predictable solar storms or asteroid impacts. However, interstellar visitors introduce an array of unpredictable variables: debris fields, electromagnetic anomalies, chemical contaminants, that our current engineering standards and risk assessment frameworks were not designed to handle. As a result, future space missions will be required to incorporate protocols capable of addressing encounters with objects and phenomena that defy previous norms, ranging from complex debris interactions to unknown chemical signatures. Missions planned within our solar system, once considered routine, may now face challenges that necessitate entirely new operational standards, safety procedures, and contingency plans suited to a cosmos teeming with interstellar traffic. The legal and ethical landscape of space exploration is also poised for transformation. Existing frameworks were crafted with the expectation that celestial objects and phenomena would originate within our solar system, and thus fall within familiar notions of sovereignty, environmental stewardship, and scientific responsibility. The arrival of Atlas, however, has raised pressing questions. Who holds jurisdiction over objects that come from beyond our starry neighborhood? How should planetary protection protocols be adapted when dealing with potentially exotic organic or biological materials? And what responsibilities does humanity bear when investigating artifacts or substances of extraterrestrial origin? These questions demand the development of new international agreements, an overhaul of space law that carefully balance scientific curiosity, planetary safety, national security, and the long-term interests of human civilization. If future interstellar visitors are found to carry embedded messages, technological relics, or biological materials, humanity will need to craft comprehensive, globally coordinated policies. These would ensure that scientific investigations proceed responsibly, respecting planetary protection principles while enabling the exploration of potentially groundbreaking discoveries. Such frameworks must also address the delicate balance between transparency and security, ensuring that information sharing does not compromise the safety of Earth or its inhabitants. The Atlas encounter, therefore, can be seen as humanity's metaphorical graduation, marking the moment we transition from a civilization confined within its solar system to one that recognizes its place among galactic communities. participating in phenomena that are on an entirely different scale. In essence, this event signals that humanity is stepping beyond the confines of its planetary cradle, ready to engage with an expansive universe filled with objects and signals that challenge our understanding. The implications extend far beyond immediate scientific inquiry. They encompass legal, ethical, cultural, and philosophical dimensions that will shape human society as it adapts to its newfound galactic role. The Atlas encounter might be just the beginning of a broader cosmic dialogue, one in which we learn that our universe is far more interconnected, complex, and alive than we ever imagined. Whether humanity has successfully passed or tragically failed this cosmic test may not become clear for many decades to come. Yet it is our responses in this critical moment, our choices, our actions, our collective judgment, that will forge patterns shaping the very evolution of our species for generations into the future. As Atlas continues its silent voyage beyond the confines of the inner solar system, gradually retreating toward the vast expanse of interstellar space, it bears more than just the chemical fingerprints of an alien stellar environment. It also carries the echoes of reflected light and radio signals, subtle signatures emitted by a young, emerging technological civilization taking cautious, tentative steps toward cosmic maturity. These faint traces might one day be detected by other interstellar travelers, who could interpret them as signs of humanity's readiness, or lack thereof, for inclusion in the broader community of intelligent life among the stars. October 3, 2025 might be remembered not merely as the day when Mars faced a potential threat from an interstellar visitor, but as the moment humanity first glimpsed its place in a universe teeming with wandering messengers, each carrying news from distant worlds. The pressing question is no longer solely what Atlas might do to Mars, whether impact, contamination, or atmospheric upheaval, but what it has already accomplished within us. Have we truly grasped our cosmic vulnerability? Are we prepared to face the implications of contact with an unknown intelligence? Or are we, in fact, blind to the deeper, more insidious shifts that this encounter has already set in motion? The greatest danger posed by Atlas might not be planetary catastrophe or electromagnetic disturbances. Instead, it could be that we have learned nothing about our own fragility, nothing about the limits of our institutions, our knowledge, and our collective capacity to understand the universe's true nature. We may remain dangerously unprepared for the next interstellar visitor that streaks across the cosmos, leaving behind not just debris or signals, but a trail of lessons unlearned. For all we have speculated about impact scenarios and atmospheric chaos, the real peril might lie in the profound realization that we have yet to grasp the depths of our cosmic vulnerability, or to develop the frameworks necessary for meaningful comprehension of our place in a universe that is far stranger, far more active, and far more perilous than our brief technological civilization has yet dared to imagine. Now, as we approach the end of this reflection, we venture into what might be called closing speculation, a contemplation of what we may be missing in our understanding of Atlas's true significance. Imagine that October 3rd has come and gone, leaving behind a tranquil, unremarkable landscape. Mars continues its ancient orbit, orbiting the Sun with a familiar rhythm, while the spacecraft monitoring the red planet faithfully transmit their routine observations back to Earth's laboratories. Atlas, the enigmatic visitor from the stars, quietly advances along its predetermined path toward the uncharted territories of the outer solar system. Its moment of closest approach to Mars now a part of history rather than a forthcoming event. Yet beneath this calm exterior, a far more unsettling possibility begins to dawn. What if our entire conceptual framework, our focus on impact risks, atmospheric disruptions, and planetary contamination, represents a fundamental misunderstanding of what we have actually observed? What if the true story of Atlas is not about what might happen to Mars, but about what has already happened to us. How it has subtly, perhaps even invisibly, altered our information systems, our decision-making processes, and our collective perception of cosmic threats. Consider the patterns of institutional behavior that have surrounded Atlas since its discovery. These are not merely technical or scientific responses. They are indicators of deeper psychological and socio-political dynamics, the careful timing of information releases, the discreet management of data, the deliberate shaping of public narratives. These are clues suggesting that something more profound may be at play. Could it be that our institutions, consciously or unconsciously, have been influenced by forces beyond our immediate awareness? Perhaps the entire focus on impact scenarios and atmospheric disturbances is a smokescreen, obscuring a more subtle, more insidious story. That we have already been silently conditioned to accept a new paradigm of cosmic reality, one that we are only beginning to recognize. In the realm of space exploration, the usual rivalry among international agencies, each vying for resources, recognition, and scientific prestige, appeared to momentarily give way to an unprecedented level of coordination during the Atlas encounter. This collaborative effort extended beyond typical diplomatic niceties, with agencies working closely across borders, a stark contrast to their usual competitive stance. Meanwhile, a remarkable level of congressional interest emerged around what should have been a routine astronomical observation campaign. Historically, when it comes to spectacular discoveries, space agencies are quick to broadcast their findings with dramatic imagery and sensational narratives, capturing public imagination and media attention. However, in this instance, their communications about Atlas remain notably restrained and measured. The James Webb Space Telescope, renowned for its revolutionary capabilities, had been observing Atlas since August. Yet despite its advanced instruments and the profound significance of studying what is arguably humanity's first well-documented interstellar visitor, the data collected remains under analysis many months later. This delay is unusual. Such a pioneering object would typically prompt rapid dissemination of preliminary findings, especially given the telescope's ability to capture unprecedented details. Instead, NASA's Science Mission Directorate has concentrated on providing technical briefings, updates on trajectory and spectral analysis, rather than the spectacular images or compelling narratives that usually accompany major astronomical milestones. Similarly, the European Space Agency, operating under different political and communicative norms, has adhered to a comparable protocol, further indicating a level of coordination that appears to transcend standard institutional boundaries. The absence of stunning imagery or immediate visual spectacle from the October 3rd encounter should not necessarily be viewed as a failure of observation efforts. Instead, it suggests a deliberate and strategic approach to information management, one that might have aimed to control the narrative and limit public speculation. If the most critical aspects of Atlas's passage, perhaps spectral signatures or subtle gravitational effects, occur in spectral bands or at resolutions that are not visually arresting or easily translated into dramatic footage, then withholding sensational imagery could well be an intentional component of this cautious communication strategy. In the world of professional astronomy, competition over discovery, publication, and media attention is fierce. Typically, scientists and research teams rush to announce their findings through press conferences and rapid publication channels, eager to stake their claim and gain recognition. Yet, regarding Atlas, there has been an extraordinary collective restraint. Preliminary findings that might otherwise have been shared with the world, perhaps even heralded as groundbreaking, are instead undergoing a more deliberate, peer-reviewed review process. This approach appears to prioritize institutional coordination and cautious verification over individual accolades or sensationalism. Adding to this unusual silence is the amateur astronomy community, which, despite having access to increasingly sophisticated backyard equipment, has produced surprisingly little independent analysis or commentary on ATLAS. Usually, dedicated citizen scientists and hobbyists are eager to share their observations, challenging, complementing, or verifying professional data. Their reticence here suggests that external observers might be under subtle pressure to refrain from competing or sensationalizing, perhaps to avoid complicating the official narrative or to prevent misinterpretation of data that could spark unwarranted alarm. This silence and restraint could be interpreted not as disinterest but as a form of coordinated information control. It's possible that agencies and oversight bodies are managing what is disclosed, especially considering that some aspects of ATLAS's behavior might be classified or sensitive, particularly if the data hints at unexpected chemical signatures or gravitational effects that could have broader implications. Congressional oversight, though generally focused on routine budgetary and policy issues, may in fact be probing into classified facets of ATLAS research that are never reflected in public transcripts. The space science committees, which normally oversee the most expensive and complex missions, such as those involving planetary observation, have demonstrated an unusual deference to agency experts regarding strategies for observation and data dissemination. This suggests a level of internal consensus, or perhaps caution, that surpasses typical transparency protocols, hinting at a broader, carefully managed approach to the dissemination of information surrounding ATLAS. According to the established principles of international space law, there exist frameworks designed to govern the dissemination and management of information concerning potentially hazardous objects in space. These protocols were originally crafted with the mission of overseeing near-Earth asteroids, cosmic debris whose trajectories and properties are relatively well understood and whose threat levels are considered within predictable bounds. However, these legal and procedural structures were not conceived with interstellar visitors in mind. Such objects, originating from distant star systems, may carry signatures and compositions that transcend the typical boundaries of astronomical significance. Their origins could reveal information, perhaps about extraterrestrial civilizations or unknown cosmic processes, that goes far beyond the scope of conventional planetary defense and scientific curiosity. If ATLAS is indeed an interstellar object bearing implications for national security or influencing international diplomatic relations, the existing treaties and protocols might prove insufficient. They lack provisions for handling the sensitive information that such a visitor might carry, data that could impact global stability if mismanaged or disclosed prematurely. The possibility that we are witnessing the first coordinated global efforts to respond to an interstellar visitor, one that holds embedded messages or advanced technology, may explain many of the irregularities observed in official coverage. The actions of space agencies and the responses of intelligence and political institutions. These entities are likely confronting challenges unprecedented in human history, operating without any established precedent or comprehensive guidelines. Beyond mere secrecy, the control of information in this context could serve purposes far more complex and nuanced. If ATLAS contains embedded messages, technological blueprints, or scientific data that humanity is not yet equipped to interpret or employ safely, a carefully managed process of disclosure might be a form of responsible stewardship. This approach would aim to gradually introduce humanity to potentially transformative knowledge, thereby preventing societal destabilization that could arise from sudden, unprepared exposure to such revelations. This process of phased disclosure could span decades, with each stage tailored to align with humanity's evolving technological capabilities and social awareness. At present, the focus on ATLAS might seem like an intriguing but routine astronomical event, an object following predictable physical laws and behaving in ways consistent with known models. However, this apparent normalcy could be merely the initial phase of a much broader educational campaign. Institutions tasked with science education and research might be quietly developing curricula and research initiatives designed to prepare society for a future where the true significance of interstellar objects is recognized. These efforts could include exploring the implications of interstellar communication, the concept of cosmic citizenship, and the responsibilities that come with understanding and interacting with non-human intelligences. Yet such preparations would only be accelerated once political and social frameworks are in place to manage the profound knowledge these objects might ultimately reveal. The notion that current research on Atlas is just the beginning might conceal a deeper, long-term strategy, one aimed at readying humanity for an eventual awakening to the object's true importance. Even if this process involves a degree of secrecy or subtlety, the underlying goal would be to ensure that when the moment of full disclosure arrives, society is sufficiently prepared to handle the consequences responsibly. Still, this entire approach presupposes that Atlas carries information or implications significant enough to warrant such elaborate, cautious coordination. What if the most unsettling possibility is far simpler and more straightforward? Perhaps Atlas is nothing more than what conventional astronomy suggests: a routine interstellar object obeying the known laws of physics, following a predictable trajectory across the cosmos. Our innate tendency to seek hidden signs or covert messages in such objects might reveal a dangerous vulnerability within our information processing systems. The ease with which conspiracy theories and alternative narratives have attached themselves to Atlas could be indicative of a broader societal susceptibility, one that exploits our psychological craving for cosmic significance and the mystery of the unknown. This susceptibility leaves us vulnerable to disinformation campaigns which can distort reality, foster paranoia, and obscure genuine threats amid the noise of speculative fiction. If a truly ordinary astronomical event is capable of sparking such elaborate and widespread speculation, then how should we prepare ourselves when confronted with actual cosmic threats or genuine messages from distant civilizations? The encounter with Atlas may have inadvertently served as a critical test, an unintentional gauge of our collective ability as a civilization to analyze and respond rationally amidst uncertainty and rampant speculation. Our reactions to this interstellar visitor, the theories we've spun, the fears we've voiced, and the institutions we've placed our trust in or suspected of deception, could reveal fundamental flaws in our decision-making processes. These weaknesses, if left unaddressed, might prove disastrous when faced with authentic cosmic dangers that demand clear, coordinated action. The rapid transformation of Atlas into a symbol, an unwitting canvas for every anxiety about government secrecy, extraterrestrial risks, and institutional competence, suggests that our information systems are more fragile than we often realize. Social media algorithms tuned to prioritize sensationalism tend to amplify dramatic narratives over factual accuracy. This creates a dangerous environment where speculation and misinformation can outpace and overshadow rigorous scientific analysis. As a result, our response to Atlas on October 3rd wasn't merely about observing a celestial object. It became a mirror reflecting our society's complex relationship with the unknown, our levels of trust and expertise, and our capacity to differentiate between authentic mysteries and manufactured crises. The lessons we extract from Atlas's passage through our solar system might be more consequential than any physical effects it might have had on Mars or other planetary bodies. Perhaps the most profound realization emerging from this encounter is a matter of timing, that our solar neighborhood exists within a vast galactic context where interstellar visitors are not rare anomalies but routine occurrences. The scarcity of such objects in human historical records does not necessarily indicate their true rarity. Rather, it reflects the limited duration of our technological civilization relative to the immense timescales of the cosmos. If Atlas marks the first of many interstellar travelers, whose detection capabilities are expanding rapidly, then the way we currently interpret and respond to these visitors could set a precedent for all future encounters. The frameworks we develop, both scientific and societal, for analyzing objects like Atlas will influence how humanity interacts with similar phenomena for generations to come. The data produced by observations of Atlas, spectroscopic signatures, orbital trajectories, emission patterns, represent the most detailed and comprehensive study of an interstellar object ever undertaken by human civilization. Embedded within these datasets could be insights that remain hidden today, awaiting future technological advancements that will reveal patterns, signatures, or messages beyond our current understanding. Decades from now, researchers and scientists might uncover correlations or signals within the data, patterns that, with more advanced mathematical or theoretical tools, could unlock profound secrets about interstellar origins or even extraterrestrial intelligence, secrets that are currently beyond our perception. The most profound discoveries stemming from Atlas's passage through our solar system may not manifest until the decades ahead, possibly not until the 1940s or beyond, as future scientific breakthroughs enable us to decode and interpret the subtle signals encoded in observations we are making today. These insights, initially opaque and perhaps seemingly insignificant at first glance, could hold the key to understanding the true nature of this cosmic visitor and the broader implications for our place in the universe. Atlas has catalyzed an unprecedented level of international cooperation among space agencies, research institutions, and even amateur astronomers, an extraordinary experiment in global coordination focused on a cosmic phenomenon that transcends national borders. The protocols and collaborative frameworks developed to share data, synchronize observations, and analyze findings might serve as vital templates for managing future encounters with interstellar objects or other celestial events that challenge our current understanding. Such a unified approach could lay the groundwork for a new era of planetary and interstellar awareness, enabling humanity to face cosmic surprises with a coordinated, resilient response. However, this collective effort is not without its inherent vulnerabilities. The very coordination that allows for a comprehensive analysis can also amplify the risk of systematic errors. If our current research efforts overlook critical pieces of information or misinterpret subtle patterns, mistakes that could easily slip through due to the complexity and novelty of the data, the widespread nature of our collaborative network might inadvertently propagate these inaccuracies across multiple institutions and nations. The same interconnectedness that facilitates a broad, detailed understanding could also make it harder to recognize and correct fundamental mistakes once they occur, creating blind spots in our collective knowledge. Amateur astronomers have played a vital role in Atlas research, demonstrating the enduring importance of distributed observation networks. Their contributions highlight the value of continuous real-time monitoring, which extends beyond the limited windows of professional telescopes and observatories. In the future, the most insightful studies of interstellar visitors may come from coordinated campaigns that meld the skills and dedication of professional scientists with the widespread reach and persistent vigilance of amateur observers, all coordinated across different geographic locations. Such a hybrid approach would maximize coverage, minimize blind spots, and enhance our ability to detect and analyze fleeting or subtle phenomena. Educational institutions, which have already employed Atlas as a dynamic real-time case study of interstellar object behavior, have begun creating pedagogical resources inspired by this extraordinary event. These teaching materials, observation protocols, and analytical techniques will influence generations of scientists, shaping how they approach the mysteries of the cosmos. The knowledge and methods developed during Atlas's analysis will serve as the foundation for scientific education and discovery for decades to come. fostering a new wave of curiosity, innovation, and methodological rigor. Beyond its scientific importance, Atlas has profound psychological and cultural impacts that may prove as enduring as its data contributions. This interstellar visitor has compelled humanity to confront its cosmic solitude in ways that purely theoretical discussions could never evoke. The simple fact that an object from another star system has entered our neighborhood has made interstellar space feel less vast and more accessible, and has rendered the possibility of alien civilizations more tangible and immediate. Public opinion polls conducted during Atlas's approach reveal shifting attitudes towards space exploration funding, planetary defense initiatives, and international scientific cooperation. These attitudinal shifts, triggered by a single cosmic event, could influence policy decisions and resource allocations for generations, shaping the future trajectory of human space endeavors. Atlas has also exposed the extent to which modern technological civilization depends on the assumption of a predictable, stable cosmic environment. Our spacecraft, communication systems, and even terrestrial infrastructure were designed under the premise that space remains essentially unchanged between major solar storms and asteroid threats. This reliance on cosmic stability underscores a crucial vulnerability. As we venture further into the cosmos and encounter objects like Atlas which challenge our expectations of a quiet, predictable universe, it becomes clear that our technological and scientific frameworks must evolve. The knowledge gained from Atlas's passage is likely to inspire new protocols, technologies, and international agreements aimed at safeguarding humanity against the unpredictable and often tumultuous nature of the cosmos. Interstellar visitors introduce a host of unpredictable variables that current engineering designs and risk assessment protocols were never intended to handle. As humanity ventures further into space, our future missions must prepare for encounters with debris fields, electromagnetic disturbances, or chemical contaminants left behind by these cosmic travelers. Protocols that have historically sufficed for exploration within our solar system, focused on predictable asteroid impacts or planetary atmospheres, may now fall short when faced with the complex dynamic environment created by objects originating from distant star systems. The existing legal and ethical frameworks that regulate space exploration were developed under the assumption that cosmic interactions involved objects from within our own celestial neighborhood. But the presence of interstellar visitors like Atlas raises profound questions about sovereignty, planetary protection, and our responsibilities as explorers. These objects may carry embedded messages, technological relics, or biological materials that challenge our current understanding of space law, demanding the creation of new international agreements. Such treaties would need to carefully balance the pursuit of scientific knowledge with the imperative to protect planetary environments, address the security concerns of nations, and manage the risks of biological contamination. Furthermore, they must consider the long-term implications for human civilization, how to explore without inadvertently introducing hazards or disrupting potential extraterrestrial ecosystems. Atlas's passage marks a pivotal moment, a symbolic graduation of humanity from a civilization confined to a single star system toward participation in phenomena of a galactic scale. Whether we have succeeded or failed this cosmic test might not be immediately apparent. The true consequences of this encounter could unfold over decades or even centuries. Yet the manner in which we respond now will lay the foundation for our future, shaping the patterns of exploration, diplomacy, and scientific responsibility that will influence our species far into the future. As Atlas ventures onward toward the outer boundaries of our solar system and eventually back into interstellar space, it bears more than just chemical signatures from an alien stellar environment. It also transmits the reflected light and radio emissions of a nascent technological civilization, signs of a species taking its tentative first steps into the broader cosmic community. Future interstellar visitors equipped with the ability to detect these signals might interpret them as messages, evidence of humanity's readiness or unpreparedness to join the galactic network. In this context, October 3, 2025 might be remembered not as merely the day Mars faced a potential threat from an interstellar object, but as the moment humanity first recognized that we are not alone in a universe teeming with wandering messengers from distant worlds. The most profound question that arises is not what Atlas might do to Mars, but what has already been altered. The long-lasting effects of this encounter on our understanding, our policies, and our place in the cosmic order. The true worst-case scenario may not be a planetary catastrophe or electromagnetic upheaval. Instead, it could be the realization that we have learned little about our vulnerabilities, about our institutional shortcomings, or about the profound dangers lurking in the cosmos. If this is the case, we risk remaining blind to our cosmic vulnerability, unprepared for the next visitor, and unaware of the delicate yet immense responsibilities that come with venturing into a universe far more active and unpredictable than we once believed. Our encounter with Atlas might thus serve as a stark reminder. The universe is far stranger, more vibrant, and more perilous than our current technological and legal frameworks can fully grasp. Without a decisive shift in our approach, the most dangerous outcome might be the silence, an ominous acknowledgement that, in our quest to explore the stars, we have failed to truly understand the cosmic symphony playing all around us. The silence that descends in the aftermath of October 3rd may well be the most foreboding sound in all of human history. It's not the silent vastness of space, something we have always acknowledged and accepted as an infinite backdrop to our existence, but rather the silence of missed opportunities, of warnings overlooked, and of questions we were too hesitant or afraid to pose. Within that stillness, Atlas continues its silent voyage back into the depths of the cosmos, carrying with it the faint, fading echoes of a burgeoning civilization, signatures of a young society that had its first and perhaps only chance to demonstrate its readiness for cosmic inclusion. Whether we have truly passed that critical test remains an open question. The universe, infinite and unyielding in its patience, will surely present more opportunities, more moments for reflection, for discovery, or for failure. The real challenge lies in whether we will recognize these moments when they come, or whether we will persist in mistaking the universe's most vital messages for mere background noise, an endless static in the eternal cosmic symphony that surrounds us. Because sometimes the most profound revelations are not announced through spectacular catastrophes or dramatic events, but emerge quietly. Subtle truths revealed in the moments we fail to listen, in the questions we choose to ignore. Perhaps Atlas, in its silent passage, has already bestowed upon us precisely what we need to survive and thrive as a spacefaring species. Maybe the gift it carries is not one of destruction or chaos, but a hidden lesson about our readiness, our resilience, or our capacity to recognize opportunities cloaked in ambiguity. The true worst-case scenario isn't necessarily that Atlas will wipe out Mars or devastate our ambitions. Rather, it's the unsettling possibility that Atlas might in fact be the vessel that saves humanity. Yet we remain oblivious to the salvation it offers, too distracted or too cautious to see the answer staring us in the face. In the grand cosmic story, the most significant victory may be one we never realize we've achieved, because we failed to listen when the universe was quietly speaking.